Okay, I think the YouTube is successfully connected now. Let me just reshare my screen. Okay, I think the YouTube is successfully. Okay, we'll get started. Everyone can hear me, right? Maybe give a thumbs up if your video's on. Yeah, okay, perfect. So welcome everyone. This is the sixth edition of the Blockchain Technology Symposium. You can see the slide, right? Not the notes. Okay, good. Um, okay, so I'm Jeremy Clark. I'm coming to you from Concordia University in Montreal. I'll start by acknowledging that Montreal is located on the unceded lands of the Kanaka Nation. We respect the continued connections with the past, present, and future in our ongoing relations with Indigenous and other people within the Montreal community. So BTS was started in 2018 by Adafe Mashatan, who's here, and Powell Pralat. The first symposium was in Toronto at the Fraser Institute, and since then it's been held in or virtually from Toronto, Vancouver, Calgary, and Montreal. So BTS is meant to sort of showcase Canadian blockchain research, and it also is designed to try and connect academia, industry, and government. Now, I'll admit that this year's program is tilted a bit toward academia, so I'll take the fine for that. However, I think all the talks that we have will be of general interest. We'll try to rebalance it next year too and try and work in more industry and government. And we hope to run it again next year in either a hybrid or in-person format. Not all those details are set just yet, but stay tuned. And if you are here, you're on our mailing list. And so we'll definitely advertise it to you once those details get set. So I want to thank all the organizers who are on the screen. So Jen, who's my co-lead and will be taking over for next year. And then Ray, Addy, Vicky on the steering committee as well. Okay, so with all of that said, I think we'll just jump in to our opening keynote. So Xiang Fu is from Hofstra University, which is in Long Island, New York. And his research is on cutting edge, succinct, zero knowledge, proof technology, lots of real world applications. I've had the pleasure to sort of correspond with him a lot over email about some of the protocols that we're both interested in. And so I'm really excited to hear his talk. So yeah, if you want to unmute and try to share your screen, and hopefully it all goes well.
All right. Is the voice okay? Where's
Yeah,
everyone?
yeah, it's
Fantastic. I'm going
good.
to share my screen. All right.
Cool.
Can everyone see my slides? Yes.
Yeah, we hear you, we see you, everything's perfect.
All right. Fantastic. So we'll get started. All right. So, hi everyone, and again, thank you, Jeremy, for the nice introduction. So, this is Sean from Hofstra University. So today I will talk about how do we produce efficient zero knowledge proofs for the financial solvency problem. All right. So actually, you might be surprised to find that actually my background was actually from formal methods of software engineering. So in the past, I do a lot of research related to model checking, symbolic execution, malware analysis, and automatic export generation, and so on. So as to how I got into this exciting field of cryptocurrency and zero knowledge proof, I later I will have a brief story to share when I talk about the zero knowledge lookup arguments. All right. So, but for now, um, I'm going to treat myself as a brand new player into the field, and I'm going to humbly sharing my findings and explorations in the field. All right, let's get started. So we know that financial solvency is not a new problem. So it matters a lot for the financial industry. The reason is that people need this to establish their confidence in the financial organizations involved. So here is a picture from almost like 100 years ago. So in the early 1930s, there was a banking panic. So basically, the public were worried about if their banks would be able to pay off the liabilities. So basically, everybody rushed to their banks and tried to cash out their lifelong savings, which in turn speeded up the crash of the entire system. Right. So unfortunately, um, the history is basically repeating itself, but in different forms. So in the last decade, we have seen the great success of the blockchain technology and the great success of cryptocurrencies. Meanwhile, we have also witnessed a lot of crashes and bankruptcies of cryptocurrencies and financial organizations. So here is a timeline of the major security incidents related to cryptocurrency exchanges. So in particular, I would like to mention the Beanstalk attack. All right, you can see that the entire 180 million assets just evaporated in 13 seconds, due to an hacking incident. Because the blockchain is basically irreversible, so you just cannot get the asset back. So apparently the solvency problem is important. So we need the proof of solvency to help the public to establish the confidence in the financial organizations, especially, for example, cryptocurrencies. Right. So this does not only apply to cryptocurrencies, but it also applies to, for example, banking systems, many other financial organizations such as mutual funds. All right. So essentially, the solvency problem is about, well, to prove that the total sum of the assets of an organization is greater than its liabilities, right? Simple like that. But in this talk, we are seeking a better answer to a simple solvency proof. So we know that traditionally, this proof of solvency is usually performed by financial firms such as auditors, but we are trying to look for a publicly verifiable proof. All right, so you might be wondering, well, why do you need a publicly verifiable proof? So the reason is that we would like to increase the public confidence in the system. So, for example, take the Madoff case as one example, who happened to be the most infamous alumni of Hofstra University. All right, so I guess everybody have heard of that. So his organization, his investment, basically has already kind of like gone on the water for many years or even for decades. But people didn't know about that. So why it happened? Because his financial auditor worked with him for decades to hide the fact that, well, his assets actually cannot cover the liabilities. So there are lots of human risks in the auditing process. So what we would like is that we would like a machine verifiable proof for the financial solvency of the organizations. But when you talk about publicly verifiable proof, then the issues of the user privacy comes into play, right? So first of all, there's something that we have to worry about the customers, because all the information such as identity of the clients, their assets, liabilities, and the logs of the transactions. So all of this information are, kind of like protected by law. So this is kind of a hard requirement that you cannot disclose the information like that. But even for these financial organizations like cryptocurrency exchanges and mutual funds, so there are also a lot of information that you want to protect during this proof process. So for example, what about the BTC and Ethereum accounts of the cryptocurrencies? So some might be willing to share these public accounts or the BTC address information, but some others might not want to. For example, especially for mutual funds, investment funds, right? So if you disclose the details of your assets, so basically you are disclosing the information of your portfolio. So people could simply copy your investment strategy for free, or they could try to front run your investment actions to try to gain advantage in the investment and so on. So for many cases, financial organizations may also want to hide the information of the total liability, total assets, and total number of clients and so on. So some would worry that disclosing this information, especially when these values change drastically in a short amount of time, they might impact public confidence in these financial organizations. So we would like to do the proof in zero knowledge. So by zero knowledge, we mean that, well, we want to provide a proof which shows that uh, the financial organization is solvent, right? So the assets is greater than the liability. But other than the claim itself, we would not like to disclose any information. We will not disclose information about the customers. We will not disclose information about the positions of all these assets, or even total liability, total assets, or the total number of clients and customers. All right. So that's the reason that we call it a zero knowledge proof. So we are clear about the problem, zero knowledge proof for the financial solvency problem. So what I'm going to do today is that we are going to do a survey of the past work. So what have already been done? So what's the state of the field? Interestingly, for all the past academic work, like research papers published in the field in the past decade, except the very first paper provisions. So basically, all of the papers fall into either of the two subfields. So either they prove the liabilities or they prove the assets. So I'm going to group the discussion of these past works into two categories. First, I'm going to talk about the proof of liabilities, and then I'm going to talk about the zero knowledge proof for the assets. So once we got a rough picture of the state of the art, I'm going to talk about one of the recent papers published by my research group, which is about how to produce instant zero knowledge proofs. So this paper appears in the decentralized finance workshop this past March. So there's some interesting stuff I want to talk about. And after that, we will go over some of the major problems or directions that we feel interested about in this field. So that's roughly the roadmap of the talk. And then I'm going to jump into the first part, the survey of the field first. So last year, Costas has already provided a fantastic talk, but his talk is mainly focused on the liabilities. So I'm going to briefly survey the past work, but most likely focusing on the most recent progress in the field. And then our efforts, most of the efforts will be focused on the zero knowledge proof for the assets or reserves. So that is the plan. All right. So let's talk about the past work in the liability source, right? So here we have a financial organization. So this organization holds a secret database of user liabilities, like what are these users and how much do we owe them. So this database is apparently a private. So no information should be leaked about this table. So usually the prover would like to make two claims. So the first claim is that, well, the total liability is some numbers. So notice that here I'm disclosing this number in clear text, but in many cases you may want to hide this even this total number in a hash or in a succinct commitment, something like that. All right. So and secondly, for each individual user, the prover has to provide a proof to guarantee that each user that, hey, the part of your liability is really counted towards the total sum. But again, without disclosing any other information about the liability database. So basically, that's the goal, that we want to provide a zero knowledge proof for liabilities. All right. So there's a secret database involved here. Okay. So the very first work, which is the provisions paper. So this is the very seminal first paper in the academia about the problem, the work by Jeremy's group. All right, so this paper appeared in CCS in 2015. So this is almost like 10 years ago. So what's this idea? Pretty simple and pretty straightforward. The idea of the provisions is to take advantage of a hiding commitment called Patterson commitment. All right. So here, let's say that the user one has a liability value 1,000. So instead of disclosing this value, we are disclosing the Patterson commitment to this value. So basically, let's say that G and H here are two group elements, like elliptic curve points. So I'm putting the real value 1,000 into the exponent. And here R1 here is just a blinding factor to make sure that the commitment itself is perfectly hiding, and also it's computational hiding, which is proved. So for every individual account, I am actually publishing a Patterson commitment like that. So how do I prove that the total sum of the liability is as claimed? What I do is I simply multiply all these Patterson commitments up. So it's like a product of all these commitments. The Patterson commitment has a homomorphic property where the resulting curve point will have the sum of all these numbers hiding an exponent. All right, so that is the basic idea. So that's how you prove the total liability. But of course, there are some other technical details, like, well, when we compute the product of all these group elements, we do have to make sure that all of these numbers hiding in the exponent, they are in the right range. Like there should be a valid 51-bit numbers for Bitcoin. This is done using a range proof, and in the provisions paper, it's done using a standard Sigma protocols and so on. So the beauty of the provisions paper is that it has standard security assumptions, discrete logarithm assumption, and absolutely there's no trust setup. All right, so this is the beauty in contrast to other proving technologies like ZK snarks, which I'm going to talk about later. So this is the very first a research paper in the field, which formally defined the problem of zero knowledge proof for liabilities, and later as well as the proof of assets. So the one potential downside of this approach is that the commitment size is linear with the number of the user accounts in the system. So it's kind of linear size. So this makes the technology not that very well suited for the blockchain technology because to store these commitments can be prohibitively very expensive. So nowadays, if you talk about BTC or Ethereum, to save 1 kilobytes, you're talking about at least between the range of $10 to $100, depending on the time, but that's very, very expensive. All right, so then people think about, well, how can we improve this? So Costas at the time at Facebook or Meta, so they have a team working on cryptocurrencies, their own cryptocurrencies. So they came up with the idea that how can we solve the problem of the linear size on the commitment? Well, why don't we organize the information in a Merkle tree, right? So if we organize the information in a Merkle tree, we only have to disclose the root node of the Merkle tree, and that apparently is constant size. So the idea is very simple. So so they ended up with a framework called DAPL and DAPL Plus. And I believe that DAPL Plus eventually appeared as a academic paper in CCS 2021. So in the DAPL framework, we put all the information, for example, hash of the user information, and also the same thing as provisions Patterson commitment to the liability into those leaf nodes. And then we just hash information up. All right. So for example, when we compute these internal nodes, you can see that this again is a Patterson commitment. Again, we are taking advantage of the homomorphic properties. All right, so this is like the sum of the liability of the two children nodes and so on. So that is the idea of the DAPL framework. So again, it has standard security assumptions, just like provisions. There's no trusted setup needed. And now improved from the prior state of the art is that the commitment size is improved to constant size. You only have the root node to disclose. So this is very nice. So basically, this approach is followed by the industry. I think the latest updates about the giant cryptocurrencies in the industry are roughly the information I got from 2022. All right, so it's almost like 1.5 years ago. So both Binance and OKS, these crypto exchanges in the field, they have published and pushed their proof of liability system into the production. So the basic idea is the same. So we have the information of the users stored in the leaf nodes, and basically we are hashing the information up. So you might be wondering that, well, what's the difference? What's the difference from the framework like DAPL or DAPL Plus? So the difference is that now the zk-SNARK system comes into place. By zk-SNARK, I mean the zero knowledge, succinct, non-interactive computational sound arguments for the proofs. All right, so that's the reason called zk-SNARK. So for example, Binance used a zk-SNARK system called Grow16, which is the currently known the most succinct proof systems with pairing-friendly elliptic curves. So, so the motivation for the Binance approach is this: there's a potential risk of DAPL plus framework, as pointed by one of the technical notes by Binance. So the point is this: let's say that the prover is very, very dishonest. So instead of skipping the user liabilities, they could potentially insert kind of a vicious nodes which carries negative numbers. All right. So when you put in big negative numbers in, you can greatly underreport to any values you like, right? Instead of just skipping user liabilities. So in theory, this malpractice could be detected, but only when the guy or the user who's the neighbor of this vicious node. So when this valid user performs the inclusion proof to see that, well, if his or her liability is really counted towards the total sum, So the kind of like well, the zero knowledge proof includes the kind of like a Merkle tree verification parse up to the root node, right? But for each of the node along the path, a range proof has to be provided to show that, hey, here is the valid 51-bit unsigned integer, positive integers that you've put into the liability. And then this negative number would be discovered. But this only happens when the guy who's on the neighbor did a check. So here's a potential problem. So how many users would perform the check? All right. That's an interesting question. All right. So Dapple Plus authors did provide a statistical analysis of the probability that, well, this thing will be discovered and so on, but we have to look at the real data. So how many users would actually perform the check? So if you look at the OKX report, I believe that at this moment, 2023, 2024, OKX has a user base of about 50 million account. So we're talking about 50 million account. All right. So for each epoch, which they release a solvency report like every month. So you got like a monthly report. So how many users actually check their liability is really counted toward the sum? This number, 1 million. So you're talking about only probably 2% of the users are making that checks. So this makes the validity of the entire scheme a little bit shaky because you would worry about if people would insert negative values and can update to the total liability to any values they want. All right, so that's the motivation for the Binance that so Binance and OKX, they are trying to provide something which is provides more security guarantee. So what they are claiming is that, okay, so I'm going to encode the construction of this Merkle tree as an arithmetic circuit. For example, our RNCS constraint system. All right. So and then I'm using ZK snark systems such as a gross extinction system to prove that this construction process is valid. So first of all, I'm disclosing the root node of the Merkle tree. I'm disclosing the total liabilities and might be even providing a vector commitment to all the accounts. And then I'm providing the correct relation between these three values. So that is the Merkle tree is constructed correctly. And then for all the leaf nodes, I have included all the numbers in the right range. They cannot be negative numbers. All right, so they are hashed up correctly, and then this is reflected correctly in the claim, the total number of the liabilities. All right, so then if you're using gross extinction system, basically you see a very, very small proof like 300 bytes, which proves the validity of the entire huge logic. So the idea is great, and it does take a lot of efforts to put into the concrete schemes. So the reason is just because of the sheer great amount size of the problem itself. So how many users does Binance have? So they have at least like 45 million accounts. So apparently this Merkle tree has to accommodate there's so many accounts, and you have to allow some additional padding stuff and so on. So in practice, the height of this Merkle tree is 28. All right. So even if the snark-friendly hash like Poseidon hash is used to prove the membership proof, the valid membership proof for each account, you need about 60,000 RNCS constraints, and then multiply with 100 million accounts, that amounts to about 6 trillion RNCS constraints. All right, so even with 100 servers, you probably need like 1.5 days to compute all the proofs. So that's what's happening with this. And in addition, you cannot put all the encoding logic of the Merkle tree into the same circuit, because the scalar field of pairing friendly curves like BN254, it doesn't actually support the size of 6 trillion. So you would really have to split the circuit into many, many smaller circuits and do it in parallel. So that is what's happening with Binance, and the system has been in production for almost like 2 years. So OKX uses a similar approach. So instead of using ZK snark, they use a an alternative technique called the ZK Stock. So the benefits is that the setup is transparent, so there's no trusted setup needed, but it comes with a larger proof size, like 1 GB. So that is what industry is doing. So let's come back to the academic. I'm just going to briefly mention the ideas. So there's a paper from a group of researchers from IBM in the CCS conference last year. So what they did is that they improved the DAPL approach. So we know that DAPL is based on Merkle tree, and the fan out is 2. So they increased the fan out to an arbitrary integer n, and replace the hash function by vector commitment. So this allows them to actually cut the size of the proof. So that's one work. And then let's talk about the most recent work. So there's another paper published by a group of researchers from the Hong Kong University of Science and Technology. So I think this paper is going to appear in the Unix Security Conference this coming August. So here I'm just going to briefly talk about its ideas. So in all the past work we have talked about, so all the users are required to check if their liability are included at all epochs. All right. But the nice thing of the noders is that if you just do one check, it guarantees the the correctness of the records, all the records in the past. All right. So this comes like a giant leap from the state of the art. Right. So you just do one proof and you can prove all the records in the past. So the idea is to take advantage of something called a hash chain. So as usual, we would encode the liability information in a record, and we would hash that record for each epoch. But the difference is that now in each record, we have a hash of the previous record. So it's like we have a chain of the pointers which points to the previous state and points to the very beginning of the starting of the blockchain. All right. So with this hash chain, what the prover provides is that, okay, so I am going to provide a ZK snark proof for this hash record belonging to the commitment of the current global state. All right. And because of the hash chain, I can convince you that, well, all the records in the past is correct. Well, but wait, you might want to, well, how would that be possible? Actually, well, this argument needs kind of like a recursive argument, because you have to reason about the validity of the previous state and so on and so on and so on, right? So what the notice paper did is that they again used the ZK snark system to prove that the transition from the previous state to the next state is valid, which means that by dropping some accounts, by adding some accounts, by making some updates of accounts, well, my global state is consistent to my claims. And this is done using the Grow16 system. And that is a 300 bytes short proof, which can be very easily verified by a smart contract over a blockchain. So that is the idea, using the hash chain and a very brief proof of proving the transitions between the states, and they can prove the validity of all the records in the past. Of course, there are a lot of technical details, like instead of using Merkle trees, they actually use RSA accumulators, and actually to encode RSA accumulators would be a very challenging task for ZK Snark research community. So I'm going to skip the details here. And you can see that the concrete performance of the noder system is great. 1 million account updates in just 3 minutes. All right. So basically, that's the state of for the field of the liability. And then I'm going to quickly go over the state of the art for the zero knowledge proof for the assets before we actually jump into the main talk here. All right. So again, past work about the proof of assets. So again, the seminal work is the provisions paper published in 2015. So our problem is this. So we assume that there is a public blockchain where the information of all the accounts will be available, and the prover has a private database of the accounts like BTS addresses, wallet addresses, and so on. And the prover wants to establish the fact that, well, the total sum of the assets is the claimed value, but the prover does not want to disclose the information about all these wallet addresses, Ethereum accounts, and so on. So that is the problem. So again, Provisions did this using the standard Schnorr-like protocol, standard security assumptions. So the only downside of this approach is that because we use the Schnorr protocol, so actually the hash operation for generating the BTC wallet address cannot be nicely modeled using the Sigma protocols. All right, so this problem was partially solved by a paper appeared in Crypto 3 years later. The idea is this. So we know that the operation for generating the public key is basically algebraic. So you're dealing with group scalar multiplications. But as hash operation can be modeled nicely using ZK snarks. So why don't we combine ideas of ZK snarks and the Sigma protocols? So the authors came up with a smart idea. They actually transformed this problem into a problem called the double discrete logarithm problem. So here still you have the secret key S sitting here, but the difference from the Schnorr's protocol is that now you have like 2 layers of the exponentiation here. All right. So that's the reason it's called a double discrete logarithm problem. This Crypto 18 paper provided a constant size proof for the double discrete logarithm problem. But the only downside of this approach is that unlike the Schnorr protocol, where the verifier could submit any random challenge alike, for the DD-log problem, the verified challenge can be only 1 bit. So this implies something which is a little bit shaky, because now you have like 50% of chances of getting something incorrect. So to make sure that it has the right soundness level, for example, 120-bit security, you would have to repeat the Schnorr-like 3-round protocol for 128 times. All right, so then this boils down to that, well, for one single proof, for the ownership proof, we end up with like 2,000 group elements. All right, so this makes it concretely not efficient. So I think that in the field of proving this BTC wallet address generation or signature verification, I think the current trend is that still we encode everything using the arithmetic circuit and put it into the ZK snark system. So we know that for the state of the art, for the ECDSA signature verification, naively, probably 3 or 4 years ago, you probably need a 3 or 4 million RNCS constraints, but nowadays you only need 200K. And for the hash operations, when you talk about SHA-2, SHA-256, 3 or 4 years ago, probably 250,000 RNCS constraints will be needed, but nowadays you only need 20,000 or 30,000. So putting everything together, we could probably accomplish this with no more than, for example, 40,000 RNCS, sorry, 400,000 RNCS constraints. All right, so put into modern desktop computer and so on. So usually you need just a couple of seconds, no matter it's growth system or Plonkish system, you just need a couple of seconds of prover time for the ownership proof for one BTC address. That's kind of a state of the art as far as we know. All right, so composite statement and arithmetic circuits, and let's look at another idea called MPC in the head. So this is probably the most recent paper in the field of zero knowledge proof for the assets. So it is using an approach called MPC in the head. It is known to have a very fast prover, but the downside is that the verifier has to be dedicated and has to stay online. It has to be interactive. So this is not a publicly available transferable proof. So finally, let's look at what the industry is doing. So unfortunately, at this moment, for most of the cryptocurrencies in the field, they are basically just simply disclosing all the wallet addresses. All right. So for example, this is what OKX is doing. So they disclose all of the wallet addresses in their ownership, and they publish a public message. So using the secret keys of their Bitcoin wallet addresses, they generate a signature. So this is standard digital signature. Everybody could use that to verify that, well, this is indeed a valid signature for that particular message. All right. So, but all the wallet addresses and public keys are disclosed. I think this might be okay for cryptocurrency exchanges like OKX, but it might not be okay for financial organizations like mutual funds. The reason is that you don't want to disclose your positions of the portfolios. So how many addresses are disclosed? For OKX, for 23 billion assets, they have about 700,000 public addresses out there. So that's what they disclose. All right. So very briefly, uh, we have spent a little bit more time than needed. So we have covered the most recent progress in both academia and research regarding the zero knowledge proof for liabilities as well as assets. Now I'm going to talk about one of the recent papers that we got regarding the proof of assets. So basically, this is a joint work between a group of students at Hofstra and also Stant at KN0x1Y. So the Hofstra team designed the instant zero knowledge proof of assets protocol we call ISPA protocol and implementation. And the team at KN0x1Y produced the implementation for the bootstrap stage of this protocol, so which uses the traditional way of proving the ownership. So we kind of combine the two parts of the work into one paper. So that's where we are. So again, so why instant? I think the reason is apparent. So for example, take the Beanstalk incident as one example. Well, the entire assets evaporated in dozen seconds. All right. So apparently, we would like the report of solvency to keep up with the frequency, the speed of the blockchain system, so that all the investors would have a fair chance to know about the situation. All right, so that's the reason we want instant zero knowledge proof. So what's different from the state of the art? So we have the requirement that we want to produce the zero knowledge proof in a matter of very short time, like the turnaround time from the moment that you got the data to the moment that the proof is generated and verified. We needed to be compatible with the speed of the blockchain, like 15 seconds for Ethereum or something like that. So it is apparent that all the past work in the field cannot meet that concrete requirement. So taking Godzilla, the most recent work in the field as one example, it's already known to have a very fast approver, but just for one ownership proof, they need 1 minute of proof time. But think about OKX, who has 700,000 wallet addresses in possession. So it will be taking a lot of time to compute all the proofs. So that's why we came up with the ISPA protocol, which I'm going to talk about. So what's different from the past work? The ISPA protocol, it has some nice properties. So first of all, the cost approver is independent of the anonymity set. So for nowadays, we know that there are at least 80 million wallet addresses out there for BTC and so on. And also the nice thing about this is that this anonymity set could grow at any time, and we actually basically don't have to do anything about it. So that's a nice property of the protocol. And in fact, the proof of cost is also independent of the owner set. All right. So once you have finished a one-time pre-processing phase, and then the proof of cost is only dependent on the throughput of the blockchain platform. So that's the nice thing about the proof of cost. And also the scheme is safer because when you generate the proof, there's no need to take out the secret keys. All right. So the concrete performance of the protocol is good. Our turnaround time is only 1 second. and we can support 1,000 transactions per second. And the entire protocol just runs on one Google Cloud server with a $5 cost per hour. All right, so that's some very, very brief summary of the benefits of the protocol. And then let's get to the idea of the protocol. So the main idea of the ISPA protocol is that actually we only have to provide the ownership proof for just only once. We have only once, all right? And then we can just take advantage of existing ownership proofs. So the ISPA protocol assumes that there is a bootstrap process where the financial organization, the prover, would have to compute all the secret keys and the corresponding public wallet, the corresponding wallet addresses, which they're going to use in the near future. All right, even though these wallet addresses never appear on the blockchain. All right, so they put all these wallet addresses in a in a private set. So this is some information that they don't want to disclose to anyone else. All right, so that's called a bootstrap process. So what will be made public is, first of all, Patterson vector commitment to all these addresses. All right, and then a Patterson commitment to the initial asset. All right, and then a zero knowledge proof and ownership proof, which shows that, okay, so as a prover, I know the secret keys, which generates all these wallet addresses, and the corresponding value of the initial total asset is correct regarding this set of the wallet addresses. So of course, there might be a lot of wallet addresses which have not been put into use yet, so their balance will be simply set to 0. All right, so this is the bootstrap process. Now, once the bootstrap process is done, for each blockchain epoch, and then we're going to reason about the changes of the balances. So we know that for frameworks such as BTC and Ethereum, all the information for each transaction epoch, are public. All right, so we have all the accounts involved in these transactions, and we can get the net changes of the balances related to each account. So what the prover does is that, first of all, it creates a secret binary vector like 1010s, which indicates that if these wallet addresses belong to the asset, like 1 means that, well, this is my asset, and 0 means that this is not my stuff. All right. So this binary vector is a secret vector only known by the prover. And then the prover discloses the Patterson commitment of this vector, binary vector. All right, and then it discloses a Patterson commitment to the total change of the balances for the related accounts. So for example, at this moment, there are only 2 accounts which belong to the asset. So the total balance change is positive 300, like I'm increasing the balance for 300. And then the prover would provide a succinct constant size proof, which shows that the sum of all the entries which have this 0-bit set, all right, so they sum up to the number which is hiding inside this Patterson commitment. All right, so once this proof is verified, then the prover could simply make an update of the total assets, again, Patterson commitment, by taking advantage of the homomorphic property of Patterson commitment. All right, so this is the main idea, and the key point is that the owner proof is only needed for just one time, and then we can just reason about each of the blockchain epoch. So, and then we'll get into some of the technical details of the cryptographic constructions that we need for the scheme. So, our starting point is starting point is not 0. Starting point is a lookup argument called the CU protocol. So what is a lookup argument? So so here we have a public. All right, so this is public. We have a public table of entries called cap T. All right, and the prover has a secret, much smaller table called a query table, lowercase t here, So what is visible to the public is the Peterson commitment of this smaller query table and a succinct, not necessarily zero commitment to this public table. And the prover wants to establish the fact that all the entries in this smaller query table belongs to this bigger, much bigger public table. So notice that this is slightly different from something like a zero knowledge set membership proof or subset proof. The reason is that both of these two tables allow duplicate entries. All right. So the beauty of the CU protocol is that after a analog and pre-processing stage, the prover cost is only linear with the size of the query table. So in terms of the group operations. All right, so there's still a FFT faster Fourier operation here, but the cost is really negligible. All right, and the verifier cost and the proof size are both constant size. So concretely, it's also very good. Like proof size is only 8 G1 elements, and the verify cost is up to 5 pairing operations, which usually takes no more than 5 milliseconds in practice. All right, so this is a CU protocol. So what does that imply? Simply, we put all the wallet addresses in our assets into this public table T, and then we put the transactions that each import into the query table T. Apparently, given the fact that you have a much larger asset table and a much smaller blockchain throughput, this can really save big for the prover. All right. So now the only problem is this. For the CU protocol, it is not zero knowledge. And also this table is public. All right. So we cannot disclose this lookup table. Instead, the first step we have to take is that we have to make CU protocol zero knowledge. All right. So the basic idea is this. So for the CU protocol, the lookup table is actually encoded as a univariate polynomial. So here, taking each element from the vector, and this lambda I is the Lagrange base polynomial. And so you sum up all these items up, and then you got a univariate polynomial. Then using the standard KZG commitment scheme, we got one single group element as the succinct and also zeros representation of the entire table like that. And then the protocol itself, it basically involves the arguments about the relations between polynomials. So I'm just making a simplified example here. So here, let's say that we have 3 polynomials, cap t, cap 1, and cap z, and we want to prove that relation like z is the product of t and y. So how do we do this? We simply ask the verifier, raise a random challenge r, and then I'm going to provide a KZG opening proof, which shows that, well, the polynomial t evaluates to this value t here at a point r, and so on for these 3 polynomials. And then the verifier could simply verify that the product of these 2 numbers are as expected. So this scheme is fine, but the problem is that even if we are doing one single evaluation here, it actually discloses or leaks information about the committed polynomials. So instead, in our zero knowledge version of the CU protocol, instead of disclosing the point evaluations, we actually disclose the Peterson commitment of these 3 values. And then we use a Schnorr protocol to reason about the product relation between these numbers. All right, so with tricks like that, we convert the CU protocol to complete zero knowledge. All right, so starting from zero knowledge version of the CU protocol, we can have a range proof. So we are able to get a 20-bit range proof based on the CU protocol. And by running 8 instances of the 20-bit range proof, we got a 160-bit range proof, because the wallet addresses of BTCs are 160 bits. And then based on that, we could have a zero knowledge negative lookup. So basically, this is about non-membership proof. So what happens is that, let's say that we got a simple table of 4 numbers, and we want to prove that 250 does not belong to that secret table. So what we do is that we simply pick up, assuming that all the numbers are sorted in the ascending order in the secret lookup table. We simply pull out two numbers in neighbors like 200, 300, and then prove that 250 sits between these two numbers. All right. So apparently, to reason about this, you need a range proof. All right. So this is how negative lookup is done, and then based on that, we have something called positive and negative lookup. So basically, given a query table, we can provide a binary bit vector table like 1010s, which indicates that whether each of the elements in the query table belong or does not belong to the secret lookup table. And then you can see that this is basically the idea of the ISPA protocol. We can just reason about all the accounts in each of the transaction epoch. All right, so that's the basic idea. So concretely, we deploy the protocol on the Google Cloud server, and then with 1 second approval time, we can support 2,000 account updates. And the verification cost is about 40 milliseconds. Proof size is 3.4 kilobytes. The scalability of the protocol is pretty good, basically inheriting all the good properties from the CU protocols. We feel that there's still a lot of rooms for improvements for the protocol because the vast majority of the proof of cost is spent on the range proofs. All right. So if we take idea of the lasso and use lighter weight lookup proofs like plookup or logup to replace the CU protocol for the range proof, we probably could get at least 3 or 4 times the speed up. All right. So that's the major part of the ISPA protocol. So the second part of the paper is about the bootstrap protocol, and this is completed by the Stant team at KN0X1Y. So the basic idea is this. So assuming that we have a large set of the secret keys, so what we do is that we feed the corresponding wallet addresses, and we feed the public information of the blockchain to a zk-SNARK circuit. And we are trying to establish the claim that, well, we know the ownership proof for each of the wallet addresses, and then the claimed initial the claimed initial sum of the total assets is correct. So this is done using the standard zk-SNARK technique called GROW16. So by Stan's team, they managed to prove about 6,000 signatures, and it cost them over Amazon Web Service about $900. So this amounts to roughly 14 cents per signature. But as far as I know, that they didn't put the most recent non-native field arithmetics into the support of the circuit. So each signature circuit actually cost them at least 2 million RNCS constraints plus extra circuits for proof aggregation and also Merkle tree proof. So I think at least there's a 10 times improvement that we can make. I think we for sure we can cut the cost of the per ownership cost to below 1 cent. All right, so that's what we got for the ISPA protocol. That is, how do we provide the zero knowledge proof of assets instantly at the frequency of 1 hertz with low cost. All right, so I think I still got less than 7 minutes. I'll try to wrap up as much as I could. All right, so let's talk briefly about the future directions and emerging proof technologies that we can take advantage of. So I think this is an very, very interesting field, but also there are some potential problems out there. For example, so for most of the academic papers here, for example, for liability, they are assuming that the prover will not over-report the liabilities because it doesn't work for their interest. And similarly, for virtually all the papers for the proof of the assets, they are assuming that, well, the prover will not under-report the assets. So this probably works for the solvency, but actually it is actually questionable. So for example, assuming that everything is in zero knowledge, so nobody can actually see anything from these proofs, right? I think there might be financial organizations interested in, for example, over-report the liability to the extent that, well, still the entire organization, we can provide the proof of the solvency, but to the extent that I'm going to skip some of the surplus profit so that I can evade tax. I think that is actually a likely a problem in the assumptions. All right. So how do we solve this? So one thing I'm thinking is that maybe it's a good idea to put in all the records of the accounting book of our organization into the public ledger, or like the commitment of all these records. And then if we use schemes like incremental verifiable computation schemes, like one proof ensures everything is okay in the past, maybe this can deter actions like full reports like that. So this is just like one idea. So another problem which I see is the formal definitions of the security properties. Like, so in the traditional world, if you want to prove that, hey, this car is mine, I got a certificate issued by the government which binds that property to my identity. But this is not a case in the world of the cryptography, right? So what we really have is just a proof of the control or the proof of the knowledge of the secret key, which generates the public wallet addresses. And even that public wallet address is not visible, right? So especially given that these proofs are non-interactive and transferable and has no binding to the identity, that could be the cases like colluding cheaters, right? So the cryptocurrency exchange could ask for a partner who generates the proof of the knowledge of the secret key. So the proof could simply forward this proof, right? Even though she does not really generate the proof, but the real owner of that wallet can still have freedom of spending from that account. So this is kind of just like an exam with no proctors, and how do we make sure that the students really submit the work, the real work, right? So there's something which should be done about the formal definition and a reasoning about these proofs of ownerships. All right, so that's another problem that I see. But in general, I feel that this is a very exciting and interesting field. So regarding some of the interesting directions to explore, there are lots of directions, but here I'm just going to list some of them. So for example, we have seen the application of a lot of crypto accumulators, right? Such as Merkle trees, RSA accumulator, and vector commitments. We have seen the application of zero knowledge set membership and lookup arguments. So one interesting direction to explore is that, well, are there any more efficient accumulator schemes out there to apply to this field, right? So another field is the folding schemes and IVC schemes. And we have already seen one nice example of the notice paper in the field of liability proof. So one proof guarantees the validity of all the past proofs, right? So we can similarly apply it to the field of the proof for the assets and so on. Finally, zero knowledge credentials. So at this moment, the cryptocurrency platforms has no identities at all. Is it possible to actually embed some hiding information of the identity into the transactions so that we can reason about other accounting properties in addition to the financial solvency? Like, can we reason about it complies with the regulations that, like, there's no money laundering activities or no activities with blocklisted accounts and so on. So if we could put the identities information into the transactions and the reason about that, it can also solve the problem of the formal definition of the proof of ownership problem. All right. So apparently there's a lot of things that we can explore. I feel that this is a very, very exciting field. I guess my time is up. So I will be able to take questions either online or offline. And for all the works I mentioned here, I put in the last slide in the presentation. And thank you.
Awesome, awesome. Thank
For,
you, thank you. That was you
all
covered
right.
a lot of ground. It was amazing. So yeah, we'll take a few questions if we have them. You
All right.
can either just unmute yourself, you can ask in chat, you can ask in question and answer. Maybe I'll just start just by asking, what do you think about like regulation, like more on the legal side? Like, do you think this is something that the government needs to step in and say that exchanges need to issue these types of proofs? Do you think there needs to be standards like sort of around like what a proof would look like? Sort of what do you think at the sort of non-technical level, if you have any thoughts?
So I'm not the expert of the legal experts, right? But here's my feel, right? So I see the point that the government wants to step in, like the famous the lawsuits case with Binance just this past year, right? And also a lot of cryptocurrencies got like the problems with the governments and so on. So I feel that for example the ZK credentials I talk about, I feel that is potential direction, right? So optionally you could actually embed these credential information, but in zero knowledge into the transaction records and so on. So when the government needed, when it falls into the regulation of a certain government, you do have to comply with the regulations. If it is optional, you just supply your proofs. But for the rest of the world, they can just go ahead without it. So that's my feeling. So essentially, I'm thinking it should be an optional thing.
Got it, got it. Yeah, yeah. There's lots of interesting work in credentials, like the Candid project from Cornell or
Yeah,
ZK login from Costas at SWE and things like
right.
that. So, okay, good. I don't see any other questions or answers. Okay, so it's noon anyway, so maybe we'll move on in the program. So thanks again very much for
My pleasure.
joining. And okay.
Hi, Jeremy.
Hi, Lily. Thanks again for doing this.
Sure, no problem. It's my great pleasure to be here and give this talk.
Awesome. Okay, we'll maybe just give people a minute to join again. If you want to share your screen in the meantime.
Yes, I will try. Can you see the desktop of mine?
Yeah, I see the desktop.
Oh, this
And now I
is
see the slide flashing.
okay. This is the title pitch
Yeah,
of my slide. Okay.
perfect. Okay, well, it's 1:15 now, so why don't we get started again? Okay, so it's a pleasure to have Lily Wei. She's at McGill University and has done a lot of work on analyzing smart contracts and looking at front-running attacks, that type of stuff. Latest papers at Oakland on front-running, I believe, and it looks like your talk today will be on finding bugs in smart contracts.
Yes, so thank you, Jeremy, for your nice introduction. So today I'm going to talk about my very first piece of work related to blockchain and smart contracts, which is called D-Archer, um, detecting on-chain, off-chain synchronization bugs in decentralized applications. So before I start to talk about this piece of work, I would like to briefly introduce myself to everyone. So my name is Lily Wei. So I am assistant professor at McGill University. And my main research area is on software engineering. So I develop tools and techniques to automatically detect bugs for different applications like Android applications, smart contracts, or IoT software. So what I mainly do is that I develop some tools that takes software as input, and we do some software analysis, either statically or dynamically. And with these tools, we will report some potential bugs in the software under analysis. And most of my research related to blockchain are on smart contracts and decentralized applications. And today I will present a work that is on the reliability of decentralized applications, considering the different execution states of the blockchain transactions. So when we are talking about blockchain and also the end users, the normal end users who use blockchain applications, they may not directly interact with the blockchain. They may not be able to directly submit transactions to blockchain. So instead, what they will do is that they will use some DApps or decentralized applications. So these DApps, they contain front-end applications like web applications or mobile applications. And these front-end applications are backed by some smart contracts. And these smart contracts are hosted on some blockchains like Ethereum. So now let me use an example to illustrate how this works. So let's consider a DApp, which is a crypto bank. So it has the off-chain front-end application, and also it has some on-chain components, which are the smart contracts. So it is a crypto bank application. So we may want to send some transactions or transfer some cryptocurrencies to some other users. So suppose we first have a user whose name is Alice, and she sent 3 ethers to Bob, and she did that through the interaction from the front-end application. And then Bob who received these 3 ethers, he wants to know like who transferred these 3 ethers to him. So if Bob wants to do this query, so what we can do to get this information is to search over the entire blockchain history and see who sent the ethers to Bob. However, this is a very costly operation because every time we want to get this information, we need to search the entire blockchain history. A typical solution for this problem in conventional software is to maintain an index of the transfer records. So if we want to do that, we have one option to store the index on the blockchain in the smart contracts. However, this is very costly. So instead, the practice of existing decentralized applications, what they do is that they maintain this index at the front end in the off-chain part of the decentralized application. So what they do is that with the on-chain state that is on the blockchain with all the transactions, they will process the transactions and cache the information to the front-end application to the off-chain part of the centralized application so that we can do the queries with relatively low cost. So every time when we want to do some queries like this, we don't need to go through the information on-chain, but instead we can just use our local index, which is denoted as off-chain states. Okay, so this is a very commonly used design of modern decentralized applications. And it is very efficient. Okay, however, using this design and this architecture, there is some key challenges because maintaining the consistency between the on-chain states and the off-chain states, it is non-trivial. So here, suppose we have a new user whose name is Danny, and he transfers 1 Ether to Bob. So when we have this transaction submitted, we may want to update the off-chain state of the front-end application. However, submitted transactions will not be necessarily finalized because of the property of blockchain. So when to update this off-chain state can be tricky for the decentralized application developers, and they can commonly make mistakes. And this is the problem that we want to look at, which is called on-chain, off-chain synchronization bugs. So here I want to first dive a little bit deeper on the challenges of synchronization. So the execution of the blockchain transactions, they are non-deterministic. So the first reason is that pending transactions are not necessarily executed. So when a user submits a transaction, it will first be put into the transaction pool, and it will be executed only if some miner pick this transaction and execute this transaction. So it is possible that if your transaction is not competitive enough, so no miner will choose your transaction, and your transaction is never executed, and it will be dropped silently. Another problem that is caused, another problem of the synchronization is caused by a chain reorganization. So some transactions, they are executed, they are included in the blockchain, but they are not necessarily finalized. Because of chain organization, your executed blocks can be reversed or invalidated. So here comes to the life cycle of transactions. So unlike conventional database software applications, when we submit a transaction, we can immediately assume that this transaction is executed and finalized. But for blockchain transactions, we cannot make that assumption. There is a life cycle of transactions. When they are created, they're first put into the transaction pool, and they are in a state of pending, and they can be dropped or they can be executed. And even after they're executed, they can be reversed. After they're reversed, it can be dropped again, or they can be executed again. And only after a certain amount of waiting time after the execution, we may safely assume that these transactions are finalized. However, when people are developing the decentralized applications, they may not always keep in mind this life cycle of transactions, and this creates some bugs. So let's go back to the previous example where we have Danny send some Ether to Bob. So if the decentralized application, they choose to update the off-chain state of their front end, as soon as this transaction has been submitted. However, this will cause some inconsistency between the on-chain state and the off-chain state. Because after it is just submitted, this transaction may not be executed and may not be included in the blockchain. So in this case, it will lead to some undesired consequences because this off-chain state are the states that are shown to the users. So with this off-chain state, so Bob will think that he has 4 ethers. And with these 4 ethers, he may further conduct some actions. Say, for example, if you want to transfer 4 ethers to Charles, but this will definitely fail. And this user will have no clue why this transaction is failing. So this is the problem of on-chain, off-chain synchronization bug. And this is the problem that we want to address. So we try to, so as I introduced earlier, many of my research are focusing on developing different automatic techniques to detect different bugs in different software. So in this research, we also want to develop a tool that can automatically expose this kind of on-chain, off-chain synchronization bugs. So what we propose is a testing framework that automatically executes the decentralized applications and identify this kind of synchronization issues. So what we did is that given the app, so we will have some off-the-shelf testing tools that are like UI testing tools, try to explore the decentralized applications just as some conventional UI software. Okay. And while we are exploring these decentralized applications, they will submit transactions to the blockchain. And in our framework, so all the transactions that are submitted by the decentralized applications will be executed in a controlled blockchain. So in this blockchain, we can control the behaviors. And what we will do here is that we will, once we receive a transaction, we will traverse the life cycle of each transaction to test whether this decentralized application is actually performing expectedly according to the change of the life cycle of the transactions. And with this execution, we further have another consistency analyzer that tries to determine or identify whether there are any inconsistencies during the execution of these transactions, during the traversal of the transaction life cycles. And if there are some inconsistencies that we detect, we will report some bugs to the decentralized the app developers. So there are 2 key components in this testing framework. So this controlled blockchain, which try to force the traversal of the transaction life cycles to execute the different states of the transaction life cycle. And the other one is this consistency analyzer, which tries to identify the inconsistencies between the on-chain and off-chain synchronizations. And now I will introduce the key idea of this consistency analyzer. So a key problem in testing is that how can we determine whether a bug exists or whether a bug is triggered? And this kind of problem is called test oracle problems. So in this context, our key test oracle problem is how to decide whether the off-chain state is inconsistent with the on-chain state. Okay, so by just looking at this question, you may have a very simple idea or a naive idea is that we may just need to check whether the off-chain state is equivalent to the on-chain state. However, this is very challenging in practice because the on-chain states are usually not one-to-one mapping to the off-chain state. Especially for some front-end applications, it can be only a projection of the on-chain states. It can only contain parts of the information of the on-chain state. So revising this naive test oracle, we will not check whether these two states are equivalent, but instead we need to have a mapping between the on-chain state and off-chain state. However, this is also not the thing that we want because it is not very practical and it may not be easily applied to all decentralized applications. So this mapping is not available and also it's app specific. However, in our tool, we want to propose a very generalizable test oracle that can work for many different decentralized applications. So to address this problem, our key idea is that we can make some observations on the on-chain states. And we want to avoid comparing on-chain and off-chain states, but instead we can only focus on the change of off-chain states within this transaction lifecycle. So we can make some observations on the on-chain state, and they are quite predictable, where for each transaction, the on-chain state of the pending state should be the same as the on-chain state of the reverse state. Because essentially, the effect of transaction when it is pending and when it is reversed, they are the same because the transaction is not executed. Another observation we made is that for the on-chain state of pending, it should be different as the on-chain state of finalized. Because after the transaction is finalized, it's executed, it is confirmed. So the effect should be observed from the on-chain states. And based on these observations, we can have a mapping or a similar expectation for the off-chain states in order to make the on-chain and off-chain states consistent. So we have this equivalent set of rules of the off-chain states, where the off-chain states of pending and the off-chain state of reverse, they should be the same, while the off-chain state of pending should be different from the off-chain state of finalized state. So based on these rules, we formalize our test oracle. So we will only check the off-chain state during the transaction lifecycle. So after we submit a transaction, we will traverse through this transaction lifecycle. We will record the off-chain state of pending, the off-chain state of reversed, and also the off-chain state of finalized. And then we will compare against these rules. And if there are any violations, we will report that there is a synchronization bug in this decentralized application. So let's come back to the previous example where we have when the transaction is pending, the off-chain state is already updated, where the Bob's index has a record from Danny. Okay, so this off-chain state is prematurely updated. And then we will also check what happens if this transaction is finalized. So when this transaction is finalized, in the front-end application, it will, so this on-chain state has been properly updated. And then in the off-chain state of the front-end application, we can see that the Bob's index, it also contains this transaction from Danny, which is 1 Ether. So by comparing this two off-chain states, so we can see that in this decentralized application, the off-chain state of pending and the off-chain state of finalized, they are the same, which violates this rule, the second rule, okay, where we define these two states, they should be different. So we will report a bug, okay? So this is how our tool can detect this kind of synchronization bugs in decentralized applications. And that's the basic idea of our D-Archer, okay? And to evaluate the effectiveness of D-Archer, so we collected 11 D-apps as our subjects, and this is a table of them. So they are all popular D-apps with various scales, and they serve for different purposes. So in the first research question, we want to evaluate the bug detection capability of D-Archer, where we want to see whether it can effectively detect synchronization bugs in the D-apps. And we tested, or we run D-Archer for each app for 1 hour, and we repeated 10 times for each experiment. And we manually checked all the reported bugs. And here is a table of the results that are generated by D-Archer. So as we can see in this table, so D-Archer covers over 70% of the call sites that are Ethereum APIs that send transactions. And it has a relatively high precision of over 95%. And it also has a acceptable high recall, which is over like 85%. And its accuracy is around 90%. So in this research question, we can conclude that D-Archer is able to detect on-chain, off-chain synchronization bugs with high precision and recall. Okay, so this is the first research question of our work. The second research question, we want to evaluate the efficacy of our test oracles. So how effective are our proposed test oracles, and can on-chain, off-chain synchronization bugs be detected using existing test oracles? So as I introduced earlier, test oracles are a key problem of testing techniques where we need to determine whether a bug has been triggered. So some traditional testing techniques, they will use some conventional test oracles like just runtime errors. So if there is a runtime error, so people will consider, okay, there may be a bug within this D-app. And using this baseline for comparison, we can show that D-Archer detects much more synchronization bugs within our 11 subjects. So here, I want to highlight the recall. So using just runtime errors as test oracles, the recall is only around 10%. So these results show that the baseline oracles or the runtime errors are not efficient since are not effective since inconsistencies between on-chain, off-chain states does not necessarily induce runtime errors. So in some cases, of course, it may induce some runtime errors, but typically the synchronization bugs are exhibited as some like state inconsistencies. Okay, finally, I want to briefly demonstrate the usefulness of our work. So we detect these synchronization bugs, and also we reported these bugs to the original app developers. And also here are some feedback that we received from the developers. So the first one is from MetaMask. So here, as we can see, they have labeled our bug report as a valid one, and they were trying to fix this issue. And also, we received some other feedback from very popular the app developers, like they confirm this issue and they assume that, or they confirm that synchronizing their applications with the blockchain backends, and sometimes these decentralized applications, they may also have some centralized servers. So syncing these different parties is a very challenging task. So that's all the information that I want to deliver about our work, the Archer, and I want to conclude our contributions as we are the first to examine the bugs in on-chain, off-chain synchronization process of the decentralized applications. And also we propose 2 effective test oracles that avoid checking the consistencies between on-chain and off-chain states, but we can effectively detect synchronization issues. And also we conducted a evaluation on 11 real-world DApps, and the results show that we have a very high precision and relatively high recall and accuracy. So that's it for my talk. I would like to thank everyone, and also here, these are my collaborators for this work. So I also want to thank them who make this piece of work happen. And this work is actually a piece of work of as a result of my postdoc study. So it's actually quite some time ago. So, but if you have any questions, I will be happy to answer.
Great, thanks. So again, questions, you can raise your hand, put them in chat. Okay, yeah, go ahead, Trin.
Good morning, everyone from Vancouver. So first, thank you really a lot for a very cogent and easy to understand topic, even though it's quite for a technical topic, and you can make like a social science study of blockchain understand like me, like it's really impressive. And following your research, it made me realize like there's many things about blockchain that more social scientists can kind of assume or don't fully understand, because there are a lot of technical intricacies that don't make it live up to it ideal ideas. So can you share some of your observation of kind of some assumption or misleading understanding that in the social science side tend to have about blockchain?
Okay, so that's a great question, but I don't think I'm not sure whether I have good answers for this. But for me as a software engineering researcher for blockchain, so one thing related to social aspect could be that we are interested in social aspects from the software engineers. So I'm not sure whether this is interesting to you, but for us, sometimes we will look into like how developers, but not only for blockchain, but they can be for blockchain, like how the developers on GitHub, they interact with each other. So whether like some like gender properties of the developers, or whether like the experience level of the developers, they can affect how they contribute to some software projects. So I think that's maybe one thing that I can think about social aspects about blockchain developers.
Yeah, great input. Thank you. Thank you for sharing your opinion.
There's one question that too, if you want to read it.
Okay. Yes. So how does dynamic testing for the app compare with static analysis like model checking for synchronization bugs? Okay, so I think this is a great question. So I believe, of course, static analysis can also be one solution for synchronization bugs, but I believe it is more challenging to use static analysis to detect synchronization bugs in the apps because it may involves static analysis for both like the front end side of the application and also the smart contract set of the application. I believe this kind of analysis between different components of the software can bring a lot of more challenges for static analysis, because in static analysis, it is very hard for us to precisely model the behaviors under different circumstances. Like it is very hard for us to capture the information of what is the code, what is the behavior of like this transaction lifecycle state. So I think that's the challenge, and I think that's why we choose to use dynamic analysis for testing to tackle this issue.
Okay, go ahead.
Hey, it's great talk. Thank you. I noticed that a lot of the GitHub examples you mentioned were DeFi. Would this approach of using oracles and the way you propose, would that work for, let's say, real world assets or connected devices? Let's say you have a sensor that's posting data on the blockchain. Would you also be able to measure the synchronization errors with your approach?
Sorry, I missed one point. Like you mentioned some other types of decentralized application other than DeFi.
Yeah, like IoT or real world assets.
Okay. Yeah, I believe it can also work for those kind of scenarios. So we have a lot of the apps related to DeFi because we chose we need open source decentralized applications as subjects, and most of them are related to DeFi. Okay, so
Right.
I think for the other types of decentralized applications, like those for IoT, I believe these kind of synchronization issues are also present. And also our technique, it doesn't have any constraints on what kind of information can be compared. So I think our technique can also be applied to those kind of the apps.
Got it. Thanks.
Thank you.
I just a quick question. So when DArcher looks at a website and it finds, like, say, the display of the balance, is that like static analysis? Is it automated, or is that just you hand coding this is where that data appears on that website?
Okay, so I think that's a good question. So we have some handcrafted rules about how to retrieve the off-chain states. But we mostly fetch the information from the databases, the local data, yet not from
You're going via the UI, you're going straight to the backend.
Yes.
And then to get the on-chain state, are you running a full node? Are you using like Infura or something like that? Or how do you see what's the latest state on the blockchain side?
So we don't look at the latest states of the blockchain. So that's
I guess that's the whole point, right?
yeah. That's the point of our Oracle design. Yes.
Yeah, sorry, dumb question.
No, it's okay. Yeah, but actually I'm not sure like which specific blockchain backend we used, because it's the implementation was mostly done by the first author of the paper, and now I can't really remember like which specific framework we used.
Yeah. Okay, no worries.
Yes.
Okay, I think we're out of time, so thanks again, Lily. And we'll move on to the next speaker. All right, so the next speaker is Majid Kabazian. Did I say that right? Sort of. The names are the most intimidating part of co-hosting something like this. Okay, yeah. So Majid is at University of Alberta, and recently saw him at Financial Crypto, and he's been at AFT and other conferences as well. And we'll see what he's talking about today.
Thank you. Oh. Can you hear me well, by the way?
Yeah, we can hear you. Can't see your slides yet, though.
Okay, sure. Second. How about now?
Yep, looks great.
Just 1 second, sorry. Should be okay now, right?
Looks good. Perfect.
Okay, good. Yeah, most prominent blockchains are notoriously slow when it comes to processing transactions. For example, Bitcoin can process maximum of 7 transactions per second. And on top of that, the confirmation time is not short. For Bitcoin, for instance, it takes on average 10 minutes or more sometimes for a transaction to be confirmed. So compare these numbers to what a custodial payment network can handle. For instance, Visa can handle tens of thousands of transactions per second, and the confirmation time is order of seconds. Another shortcoming of Bitcoin, at least when it comes to micropayments, small payments, is that the transaction fee is not very small. For example, if you want to buy a cup of coffee, let's say for $4 or $5, it doesn't make sense to pay $2, $3 of transaction fee. Now, all these points, all these shortcomings means that we cannot use Bitcoin for day-to-day transactions, small transaction, micro transaction. Even if you are okay with paying like $2, $3 a fee for a cup of coffee or waiting 10 minutes, still not everyone can use Bitcoin, because at the end, there's a small number of transactions that Bitcoin blockchain can process per second. So several years ago, the Lightning Network was conceived to address these issues. The main idea behind the network is to do the transactions outside the slow Bitcoin blockchain. Of course, outside the blockchain, parties do not trust each other. So what the Lightning Network basically does is that it goes to the blockchain whenever there is an issue, whenever, for example, some party cheats, and uses the Bitcoin blockchain as a judge to solve the issue. So that's the general idea of the Lightning Network. But to see how this idea works in a little bit more detail, I need to first cover some basics of Bitcoin. Probably many of you already know about that. And after I do that, I'll go into some details of the Lightning Network. Yes, so again, the Lightning Network's idea is to use the blockchain as a judge. And this idea is, by the way, is used by many other solutions called layer 2 solutions. But the way the Lightning works is a bit different from the other solution. And this is basically layer 2 solution of the Bitcoin blockchain. So after I cover the basics of the Lightning Network, I will, if I have time, I will go through one of the earliest contributions we had in this area. And if you don't mind, I'll answer questions at the end, because it seems that I don't see the chat box. I noticed that there was a question.
Sorry, it was just me. I was just saying you are in presenter view. It's not a problem. We can see your slides, but we can also see your notes. So
sure, let me
just you whether want to fix that.
Okay, so let me just quickly do that one more time. Thank you.
Now it looks good, just the slides.
Excellent. Okay, good. Okay, so yeah, I'll start with some basics of Bitcoin. So by the end of this talk, if you don't know much about Lightning Network, hopefully you get some good ideas, high-level picture of how the network works. Okay, so yes, in the Bitcoin blockchain, a transaction has inputs and outputs. The input tell where the money comes from, and the output determines where the money goes to. For example, in this transaction, by the way, can you see my cursor moving?
Yeah, we see it.
Okay, yes. So in this transaction, as you can guess, the money comes from Alice and goes to Bob, and the amount of money is 1 Bitcoin. Yes. So if this transaction goes to the blockchain, if it's placed into the block, Bob will have 1 Bitcoin that he can spend later on. Let's say sometime later, Bob wants to pay 1 Bitcoin to Carol. To do that, Bob can create a transaction. Oh, by the way, in practice, a transaction looks more like this one. The output, the amount of output is not exactly the same as input because part of the money goes to the miner as a fee, as a transaction fee, but I'm going to ignore that small transaction fee. Okay, so if later Bob wants to spend that 1 Bitcoin, let's say pay it to Carol, he can simply create a transaction like this and send it to the blockchain. So this second transaction, when it goes to the block, spends the output of the first transaction and gives the whole 1 Bitcoin to Carol. Now, an interesting question here is, can Bob spend only part of this 1 Bitcoin output of the first transaction, say 0.4 Bitcoin of it? Well, the answer is sort of no. If Bob wants to spend this output, it has to spend it fully. It cannot just spend part of it. It has to be spent fully. But what if Bob wants to send less than 1 Bitcoin to Carol? Well, in that case, Bob can create a transaction like this. So this second transaction on the right is almost the same as the previous transaction, just like the previous one is trying to spend that output. But unlike the other one, it has two outputs. One output pays 0.4 Bitcoins to Carol, and the other output pays the remaining of 1 Bitcoin, 0.6 Bitcoin back to Bob. So this is the way Bob can spend part of this output. Okay, so I guess my main point here is that after one transaction spends the output of this one, no other transaction can spend this output. If another transaction tries to spend this output after the second transaction is in, that transaction will be considered double spending and will be rejected. So again, an output can be spent only once. Okay, so in general, we can program the outputs of a transaction in Bitcoin using a stack-based language. This language is not Turing-complete language, meaning that you can do anything you want with it. For example, it doesn't have for loops, but it doesn't mean that you cannot do much with it. You can do a lot with that language. For example, you can program the output of a transaction to have a time lock. For example, in this transaction, you see a time lock. If I set the value of time lock to 8 hours, it means that Bob won't be able to spend this 1 Bitcoin within 8 hours after the transaction goes to the blockchain. So this is one example of programming the output of a transaction. Here's another example. This transaction has 2 inputs, but what is special about the output is that it has 2 colors. Basically, what it means is that 2 signatures are required to spend this output of the transaction. In other words, both Alice, blue color, and Bob, red color, they both need to sign a transaction to spend this output. Neither of them alone can spend this output. So we can do stuff like that to the output of a transaction. Okay, so with that introduction to Bitcoin, let me now explain the Lightning Network through a simple example. Suppose Alice buys coffee from Bob almost every day before she goes to work. Normally, for each purchase, a transaction has to be placed on the slow blockchain, which is a lengthy and expensive process, especially for buying a cup of coffee, right? So a key idea of the Lightning Network is that, as I mentioned before, not all this transaction needs to be spent on the blockchain. Okay, so most of these transactions, almost all of them, can be done outside the blockchain. The challenge is that Bob and Alice don't necessarily trust each other. Okay, so to handle this, first Alice and Bob create a payment channel by basically simply sending this transaction to the blockchain. So look at this transaction. There is only one output. Alice pays 1 Bitcoin, and the output needs 2 signatures. So both Alice and Bob can spend from together. Both signatures are required to spend that output. Now, after this transaction, which I'm going to call it the opening transaction, goes to the blockchain, we say that the channel is open. So as soon as the channel is open, Alice can start paying Bob off-chain, outside the blockchain. For example, when Alice buys the first cup of coffee, she will give this transaction to Bob. Okay. This transaction is basically spending that output of the opening transaction. It has only one signature, Alice's signature. So if Bob wants to send this transaction to the blockchain, he has to apply his own signature to the input. But anyway, Alice is paying 1 millibitcoin to Bob for that coffee, and the remaining of the balance goes back to Alice. Now, the important thing is that Bob is not going to send this off-chain transaction to the blockchain. Bob simply saves this transaction for later. So second day, Alice buys a second cup of coffee, and this time Alice gives Bob this transaction, which is an updated version of the previous one. And this newer version, Alice is paying Bob 2 millibitcoin instead of 1 millibitcoin. And the story continues. Let's say after Alice buys her 100th cup of coffee, Bob decides to close the channel for whatever reason. Maybe Bob is retiring or is going away, and he decides to close the channel. To do so, Bob can simply sign the latest off-chain transaction that he has received from Alice. So it's going to add his signature here. Okay. Now, after that, Bob sends this transaction to the blockchain. Okay, so the transaction is valid because it has 2 signatures in the input, so it can really spend the output of the previous one, the opening transaction. And as a result of that, Bob will receive 100 millibitcoins for 100 cup of coffee, and Alice gets the remaining of the balance. So as you saw over the past 100 days or so, almost all the transactions didn't go through the blockchain. Only the first transaction to open the payment channel went through the blockchain. And at the end, another transaction went through the blockchain. The remaining ones were done outside the blockchain. Okay, now at this point, you may think that think of some possible breaches and shortcomings with the method I just explained to you. For example, you may say, what if Bob goes away as soon as the channel is open? Okay. If as soon as this transaction goes to the blockchain, let's say Bob goes away, the problem would be that the Alice's money will be stuck forever. And that's an issue, right? So this is one problem. Another problem you may think of is that Bob may decide to send an older off-chain payment to the blockchain instead of the latest one. Well, for this particular scenario, Bob should be stupid to do that because the older off-chain transaction give less money to Bob, right? So Bob doesn't have incentive to do that. But in more complex channels, specifically duplex channels, in which both Alice and Bob can pay each other, something like that can happen. So one party can submit an older off-chain transaction to the blockchain and cheat that way. Okay. So the Lightning Network tries to address all these issues, basically addresses all these breaches, and also makes the channel duplex. As I say, in duplex channel, both parties can pay each other. Now, when it comes to duplex channels, one party may cheat by sending an older version of off-chain transaction to the blockchain. And the way the Lightning Network handles that is through a mechanism called punishment mechanism that I will gonna explain soon. Now, in addition to all this, the Lightning Network shows how Alice can pay Bob, even when Alice and Bob do not have a direct payment channel between themselves. So imagine this network of payment channels. In this network, Alice and Bob are connected not directly through some other channels. And in the Lightning Network, there is a mechanism to make a payment from Alice to Bob by finding a path using routing algorithm and transferring the fund through that path. So there's a lot of things that the Lightning Network does. Okay, so let me start by explaining the duplex channel. To the first approximation, here's how a duplex channel created, basically. So just like the previous case, we need an opening transaction. In this opening transaction, both Alice and Bob are contributing to the payment channel. Alice is contributing 1 Bitcoin, Bob is contributing 1 Bitcoin. And as before, the output requires joint signatures. Okay, so but the difference now is that the inputs of the opening transactions are not signed. So this opening transaction is not valid yet. They don't have signature. It doesn't have the signature of Alice and Bob here. So before adding the signatures to the inputs, what they do, Alice and Bob, what they do is that they exchange what is called commitment transactions. So this is a copy of Alice, this is a copy of Bob. Both this commitment transaction can spend this output, okay? They have the signatures, but they are safe because the parent transaction, this one is not valid anymore. So these two copies are not valid as well, but they have the required signatures. Okay, so after they exchange these two commitment transactions, they are safe to go and apply these signatures to the opening transactions. Now they are safe. Why? Because if one of the parties, let's say Alice, goes ahead and publishes this transaction on the blockchain and goes away after that, Bob is safe because Bob can submit this transaction to the blockchain. It has the two signatures, so it can spend that output, and Bob will receive his part of the money. So it solves the first breach. So if one party goes away, they are safe. The other party is safe. Now, one thing that you may notice is that one of the outputs in this commitment transaction, in this copy, this output, and in Bob's copy, this output is not circle, is a hexagon. It's because that output is special, it's programmed in a special way. So let me open up that hexagon so you can see what is inside of it. Okay, so again, on the top, we have the opening transaction, which is on the blockchain. This is the commitment transaction. I'm opening this hexagon so you can see inside. So what basically this input does, it offers two ways of spending the money, this 1 Bitcoin. One way is on the top, and needs only one signature, Alice's signature, but it has a time lock. So Alice can spend this output, but after a certain amount of time, not right away. The other way to spend this output is to provide two signatures, Alice's signature as well as Bob's signature. And if somebody has these two signatures together, it can spend this output right away. It doesn't need to wait. So one way has a time lock, the other way doesn't, but needs two signatures instead of one. So that's the output of it. Now, suppose that Alice purchases something from Bob. Okay, so they open the channel using this one. And Alice, sorry, let me go back. Alice wants to spend some money to buy something from Bob. To make the payment, Alice and Bob will update the balance by creating a new commitment transaction, something different from this one. So they update the values here. But before doing that, Bob needs to be sure that Alice is not going to submit this transaction to the blockchain in the future. Bob, basically, Alice has to cancel this transaction somehow. But there's no way to cancel this transaction. Bob cannot ask Alice to delete this transaction. Alice may not do so. So for this, to make sure that Alice doesn't cheat in the future, what they basically, the Lightning Network does, it offers a punishment transaction to Bob. Basically, Alice says, okay, in the future, if I transmitted this transaction to the blockchain and I cheated by doing so, you can submit this transaction and punish me. How? Let's see. Alice goes ahead and submits this transaction to the blockchain, this old transaction, which is not supposed to be submitted there. Now, part of the money is saved to Bob because this output can be spent only by Bob. Now, how about the other one Bitcoin? Well, if this happens and Bob notices this transaction, Bob has some time to react. Because remember, Alice cannot spend this 1 Bitcoin right away. There is a time lock there. Okay, so what Bob is going to do is to use this punishment transaction that he received from Alice, will add his own signature to it, and submit that transaction to the blockchain. And that transaction, because it has 2 signatures, can spend this output right away. Okay, and Bob will get this Bitcoin as well. He got the other 1 Bitcoin as well, so it means that Bob got all the money on the channel. So in summary, if Alice cheats, Bob will get the whole money. So Alice doesn't have incentive to cheat, basically, because if she does, she loses all the money. Okay, so we have done a lot of contribution in this area. I'm going to explain, since we don't have much time, I'm going to go through one of our earliest contribution, in which we basically discovered and addressed a potential breach. In this breach, one user, say Alice, sends an old transaction to the blockchain and then bribes the miners to ignore the punishment transaction. Okay. Okay, so let's see how it works. Okay, so again, this is the opening transaction that's on the blockchain. And on the left side, you see the old commitment transaction, off-chain transaction, and the right side is the latest one. So the latest one has the true balance. The true balance is that Bob has 1 Bitcoin, Alice has nothing. This is an older one, which gives 1 Bitcoin to each party. Sorry, 1 Bitcoin to Alice, 0 Bitcoin to Bob. This is not the right balance. Okay, so assume that Alice goes ahead and submit this transaction, the wrong one, the old one, to the blockchain. Of course, we have a punishment mechanism by the Lightning Network. So yes, Bob has this punishment transaction, which he will publish to the block. He will send to the miners. Okay, but what if Alice does this? What if Alice creates a transaction like this? Now, let's compare these two. Both of these transactions are trying to spend that 1 Bitcoin. This one has the advantage of having 2 signatures, so it can spend this output right away. This one has a time lock, okay, because it has 1 signature, so it cannot spend that output right away. Now, but this one has an advantage. It gives a lot of money to miner as a transaction fee. Okay, 0.7 Bitcoins to the miner. So if there's only 1 miner, for a second, assume that there's only 1 miner in the blockchain, Bitcoin blockchain. That miner sees these 2 transactions and has to make a decision. One of them is valid right away. The other one will become valid, let's say, in 8 hours. But that one will give a lot of money to the miner compared to the first one. So if you're a miner, and you're a rational miner, you want to maximize your money, you will wait for 8 hours, specifically knowing that this wait is not against the Bitcoin consensus protocol. nothing prevents miners from waiting, from not putting any transaction into blocks. Miners can indeed publish empty blocks. So a miner may do so if there's only one miner, but we know that in practice there are a lot of miners, right? So one miner may decide to wait for 8 hours, but doesn't know if some other miners will go ahead and publish this transaction. If somebody else publishes this transaction, this output will be spent fully, and this one becomes double spending, becomes invalid. Okay, so there is a nice scenario here. Do we think that the miners will wait for this transaction with huge fee to become valid in 8 hours, or do they go ahead and just collect a small transaction fee from this valid transaction, with this transaction which is valid right away? Okay, so to understand what may happen in practice, we use game theory. Before I talk about some of our results, let me just define a couple of things. First, the mining power of a miner is a number between 0 and 1. It's basically a probability, the probability that the miner adds the next block to the blockchain. So if the power of a miner is 0.2, it means that the miner has 20% chance of mining the next block. Of course, the more resource the miner has, the higher its mining power is. Okay, so the other thing is that I call a miner powerful if its mining power is greater than this threshold, this ratio. This ratio is the fee of the punishment transaction over the fee offered by the bribe transaction. So this fraction is usually small because the bribe transaction offers a lot of fee. For example, this transaction, this threshold could be 1% or even smaller. So yes, again, if the mining power is greater than this, for example, if this ratio is 1% and the mining power is more than 1%, we call that miner powerful. Okay, so we consider a few cases. Maybe I can mention a couple of them here. In case 1, we assume all miners are powerful. For this case, we show that there is an equilibrium in which all the miners will follow the bribe. All of them will follow the bribe. No matter what's the value of the time lock, they will follow the bribe and ignore the punishment transaction. And let me explain this a little bit more because it's not a difficult case. Yes, so consider a powerful miner, and suppose that its mining power is P. Since it's a powerful miner, by definition, P must be greater than this ratio. Now, if I change this inequality a little bit, I get this. Okay, so on the left side, basically what I have is expected gain from the bribe. If the miner waits until the bribe transaction becomes valid, with that probability, the miner will get this fee. So that would be the expected fee the miner will collect in the future. On the right side is the fee of the punishment transaction. So if the miner, one of the powerful miner deviates from that equilibrium and decide to go for the punishment transaction, in the best case scenario, that miner will collect this one, which is less than what he expects to collect in the future. So you can easily see that it's not a good strategy for the miner, because the best case scenario for that miner deviating from equilibrium is less than what the expected value of the gain the miner will have in the future in 8 hours or so. Okay, so that was case 1, where all the miners are powerful. It's not a practical case because we know that there are some miners in practice all the time that are not powerful. So because every node can become a miner, right? So in the second case, when there are some weak miners, we show that the dominant strategy of every weak miner is to refuse the bribe all the time. So weak miners, no matter what, they always refuse the bribe. So that's bad news for powerful miners, because if powerful miners decide to wait, let's say, for 8 hours, within these 8 hours, weak miners may put the punishment transaction into the blockchain, and the bribe transaction becomes invalid, right? So what happens now? Do powerful miners wait, or do they just go ahead and refuse the bribe? Well, the answer is that it depends on the amount of time lock. If time lock is large, for example, if time lock is, let's say, 1 month, oh, well, the powerful miners are not probably going to wait for 1 month, because within this 1 month, this weak miner have plenty of time to publish the punishment transaction. So yes, it does make sense that the decision of powerful miner depends on the time lock. So we devised an algorithm to figure out for what time lock values the powerful miner will wait, for what time lock values they don't wait. So we decided to get some numbers from the Bitcoin blockchain itself. We collected some numbers from through a range of blocks. Actually, my student basically did that, and using those numbers, we calculated the mining power of each miner at the time. So for this number, assume that the bribe offers 100 times more money than the transaction fee of the punishment transaction. For this assumption, we'll get that this fraction will be 1%, because bribe offers 100 times more fee than the punishment one. And based on these numbers and running our algorithms, we came out with the conclusion that the amount of time lock should be at least 8 hours or more to incentivize powerful miners to refuse the bribe all the time. Weak miners always refuse the bribe, but to convince the powerful ones to refuse the bribe right away, the amount of time for time lock should be at least 8 hours for these numbers on the right side. So in practice, these numbers change, they are dynamic. So if we want to be more sure that powerful miners do not participate in bribing, maybe we have to increase this number to more than 8 hours, or offer more fee in the punishment transaction. If you look at the payment channels in the Lightning Network, you will see that part of the channel money is reserved. So I assume that part can be used, they reserve it for a situation like this. If something goes wrong, they can offer that reserved money as punishment fee and increase this ratio, and through that incentivize the powerful miners not to wait. Okay, so either increase this one or increase the value of this ratio. And that brings me to the end of the talk. Yes, so that contribution that I mentioned at the end of the talk comes from this paper that we published a few years ago in the Proceedings of Financial Cryptography, together with my student and Roger from ETH University. Thank you.
All right, awesome, thanks. So again, questions, I think everyone knows the drill. Chat, raise your hand. I'll ask you sort of more of a high-level question, not related directly, but just more about Lightning in general. So the main sort of impediment to it seems to be that you kind of have to lock your funds up ahead of time. So it's sort of like a prepay model, right? So if I want to pay my cell phone bill for a year, I have to have like a year's worth of money now to like lock up. Is that like in practice, do you think that's like a major stumbling block, or is it just that the payments will be so small that it doesn't matter so much?
You have to think about, if you are thinking about a single payment channel, you can think of the future. If you are forecasting that you're going to spend $100 at most in a couple of years, it is the amount of money you should probably put there. You don't want to lock a lot of money for obvious reasons on the channel. But in practice, we have ways to efficiently put balances into those channels. For example, we can do rebalancing or this kind of stuff in the Lightning Network. But yes, that's a very important thing to have in mind, how much money you want to lock, because that gives you the flexibility, gives you the power of how much transactions you can do off the chain. Yes, that's probably the main bad thing about the Lightning Network. You have to lock money.
Right. Okay. Loic, yeah, we can take one last quick question.
Hey, my question is, what got you interested in studying Bitcoin? Usually people, they study like DeFi and smart contracts and things like that.
Yeah, so this is a good question. This is an old, basically, part of my research. This is what brought me actually to the blockchain area. So a long time ago, by a long time, in 5, 6 years ago, I wasn't much into Bitcoin and blockchain. And at the time, DeFi wasn't like mature enough, I would say. So, and I wasn't very much into blockchain because I thought that, especially Bitcoin, I thought 7 transactions per second is nothing. You can do nothing with it, basically. But I got to know this idea of the Lightning Network and the possibility of doing lots of transactions. And that made me interested in the blockchain initially. And that's why most of my initial works were related to, not Bitcoin, actually, to the Lightning Network.
Got it. Thank you.
No problem.
Okay, great. There's one more question in the chat. Maybe I'll just have you answer it in the chat, and we'll keep going.
Thank you.
So thanks so much again. Okay, next we have Marian Hamayan. Hopefully I say that okay. Who's at the University of Ottawa. So it wasn't until I like sat through the whole morning that I realized that it took a long time to get to social science. So anyways, thanks to everyone for hanging on if you aren't technically minded. But anyways, yeah, go ahead.
So I also wanted to apologize. I'm like on day 2 of recovering, or well, day 2 of my cold. So that's one thing. Let me just try and share my screen quickly. Here we go. And it's also cool that like a lot of you, like this was actually kind of a good segue into we were sort of talking a little bit about Bitcoin, and a lot of the talks were very, very technical. So I will be talking more so, it's sort of like the Tracy Kidder sort of a thing where, there's engineers, and thank you so much, Jeremy, for inviting me to this, because I wasn't sure how to go about this talk initially, because I knew that some of the audience was very technical and from engineering, computer science backgrounds. And so I will be focusing more so on, let's say, the culture around Bitcoin and a lot of the space, right? And some of the more ideological underpinnings of the space. So this was a cool article in Wall Street Journal. I think it was last year, or may have been, like, time goes really fast. Like it's like dog years when you're in the crypto space. And this idea of like the crypto party is basically over now. There's been like a lot of crashes and bull runs over time. It's also interesting. So I started my research into Bitcoin when I was a PhD student, and I was based at York University in Toronto. And so it was also 2014 was like a time when Ethereum was also starting off. And so back then it was like, obviously not worth what it is right now. But like people who got introduced to crypto and the space in 2020, their idea is basically, you're just flipping monkey JPEGs, or all you think about is SBF having a grand time in the Bahamas. So there's that element that's also there. And like the question that I started out with was basically, how do we make sense of what is Bitcoin? And back when I was doing my PhD, I'm an assistant professor now, but it's been like a big part of my life at this point, doing research in the space. It's basically, how do we make sense of what Bitcoin represents? And back then it was really hard to kind of, because it does bring together a lot of people, from whether you're an economist or you're a game theorist, or, you're a computer science person or a cryptographer. So it brings together a lot of different people, and they all have very different motivations. And so for me, based at a business school, like my idea was sort of looking at Bitcoin as a bit of a decentralized brand. And the way that I went about doing this is basically ethnographic and ethnographic work, which is basically you talk to people, you do a lot of interviews, you spend time in the community and get immersed in the space. And so you sort of see the offline world where people are gathering at meetup events, or they're doing conferences and stuff. And then also you study sometimes the same, or a lot of the people in the space are obviously anon. And so you sort of see the space you know, how the conversations are happening on different like platforms online, because that's where a lot of the culture obviously starts. And the way that I like to think about it is Kevin Kelly was one of the Wired magazine editors back in the day, and he had this idea of the hive, or the hive mind, basically. And it's this sort of concept of how people online can gather together, and it's really hard to kind of shape that conversation. You know, the hive kind of is, as he puts it, it's like irredeemably social, and it's sort of like a collective intelligence of like how we're going to shape the conversations around a certain thing. And we already know, in the social sciences, and especially in consumer research, there's this been a long-standing idea of like how technology affects us, and how we sort of have this almost controversial, you know, relationship with technology, where we're sort of like, we like it, but then we're also scared of all the bad that it can do. And so I was sort of looking at Bitcoin and crypto in general as like these pockets of decentralized brands that are sort of shaping up over time. And I was focused on how the social memory, like if you can think about, there's almost like an analogy with like AI systems, like, you know, they're learning, they're sort of like, they have a lot of different points of information that they take data from, and they keep on learning. And that's sort of like the social memory. Like even with like ChatGPT right now, you might be noticing it says memory updated. And so you can sort of see the social memory of a brand like Bitcoin kind of emerge on these different platforms. And then also, you know, from different sources where, you know, you've got these meetup events that are happening, you know, material objects where people are sharing, you know, merch basically. Or you have these Bitcoin embassies, like Montreal used to have a Bitcoin embassy, and the guy has now moved to Costa Rica. And he's also like, you know, you've got all of these like libertarian ethos that kind of come into the space as well. So there's a lot of like how the hive mind kind of develops over time. And I think I'll be giving like a broad sense of like, what are some of the ideological themes that come up? I feel that community is a very tricky word. Community is a very popular word in branding literature and stuff, but it's also hard to, like, you know, some of the developers that I talk to, they're always like, Bitcoin is kind of like an anti-community because everyone is kind of working against each other. It's sort of like an adversarial relationship as well. So you have, community is not really a good construct for thinking about it. It's more so you have these different people who have very different objectives. You know, you've also got like the whole Bitcoin maxis, you've got Ethereum maxis out there and stuff. So you've got like these sort of really cool conversations that are happening. And then there's also like, you know, we talk a lot of times about like crypto, but there's always been like, before that, there was, you know, obviously Bitcoin kind of started it all. And the idea of digital cash had been around for a very long time. But there's also like, you know, there's been a lot of different kind of utopias and dystopias that are attached to the space. And I think like I've sort of gone over this already, but you know, there's a lot of collaborative work that happens when you are constructing different brands. But one of the things that I really kind of enjoy exploring in the Bitcoin space is the kind of different utopias that people are trying to create. You know, and utopian ideas kind of like are centered. They've always been a part of technology. You know, we imagine these worlds in which, you know, we'll conquer Mars, or, you know, like Elon Musk, for example, has a lot of different utopias that he tries to represent. And then you've also got like these spaces where you can experience utopia. Like, for example, Burning Man is one of those places where people gather together and they kind of, you know, they're also on drugs, but that's part of like, you know, finding a little bit of utopia and building a different city. And we've sort of seen this happen with Bitcoin over time, where, you know, it's sort of gone from this like fake money, nerd money, magic money into, you know, this conversation around like sound money. And one of the interesting things, like if you look over time, like representing Bitcoin was also so hard because Satoshi basically disappeared. And if you like following like heist and all of those things, you might have, you know, followed like the Newsweek journalist who was trying to, you know, focus on Dorian Nakamoto, and he was, you know, they were like chasing and stuff. So it's like there's been a lot of narratives that make the brand very, very interesting. And there's also been like, it comes out of this, cypherpunks manifesto. You had Tim May and Eric Hughes who were talking about having privacy. And that's sort of like one of the things that motivated a lot of like early people in the space. It was about having privacy like that, and escaping surveillance states, basically. And even like you see a lot of people in the Bitcoin space right now, they're all celebrating Julian Assange being, like set free, essentially. And so there's like a lot of those ethos that kind of underpin how these conversations shape up. This was a Bitcoin developer that I did an interview with, and obviously names have been changed, but like he was basically talking about how in this world that we live in, our data is the only thing that we actually, we're sort of like, that's the only thing that makes us who we are. And then giving up that information to a lot of, whether it's social media or different platforms, it's not always the greatest thing. And so he sort of talks about like why he's so motivated to work on Bitcoin. Like that was sort of like the ideological underpinning of like why he was motivated to work in the space. And he also, it's interesting, like he was talking about in the interview how when Silk Road happened and there was these like hearings about Silk Road on CS-SPAN, he was super happy because he basically realized that, hey, I can, come out and be more public about the fact that I'm involved and working in the, and developing code for Bitcoin. There's also some of these futures that a lot of the developers can imagine. Sometimes they do tend to be somewhat, it's like the person that I was having a conversation with, I was like, would you live in a citadel? Like there's this idea of like living in citadels. And this was especially happening when Bitcoin was going through its like the more recent like 2020, 2022 like bull run. There's been like multiple, obviously. So this was a conversation we were having around this time because people on Reddit were like talking about creating citadels. And I was also noticing some of the people that I knew in the space, they were scraping all of their data on Twitter or, whatever footprint they had on platforms. They were sort of like getting rid of it and kind of going dark, so to speak, and not, sort of getting rid of those identities. And so they were sort of disappearing into the abyss as well because, they had obviously become very rich. But this person that I was speaking to, he was basically sharing how he would end up living in this missile complex and he would develop that. And this obviously comes from like some of the more libertarian elements in the space where, you basically have this idea of you have to be responsible for the, apocalypse that might happen in the future. But they're also very, very positive about what the future will hold. And this person is also into, the longevity space and stuff. So, biohacking, all of those things. Excuse me. And I won't go too much into detail about what the citadels are, but if you start Googling this, it's sort of like this idea of creating these worlds where only people who have a specific amount of Bitcoin will be able to live in these spaces. You can also have like, there's been some examples where people have experimented with living out on the ocean, seasteading has become very popular. And people are sort of, and this is something that I noticed, especially during the COVID lockdowns in 2020 and that period where a lot of the meetups, obviously they all went virtual, but then when in-person meetups resumed, a lot of people were talking about moving away from, Canada and the US, and they were sort of going off to these islands in the Caribbean. Some of it obviously has to do with like saving on taxes, but there's also like almost creating these like societies from scratch. It's kind of like the 1960s dream that people used to have in California. There's also been like one of the key motivations, obviously, for a lot of people in the space has been sort of the skepticism of governments as well. Like, there's always been like this person that I spoke to, he was sort of talking about how his family had to experience the Holocaust and they, sort of smuggle their family, like basically the valuables. They had him like, they had like little kids go through, not go through the metal detectors back then. So they would sew the jewelry in there. And so he talks about how, the experience of losing everything kind of sort of sensitized him to how much he wanted to work on Bitcoin because it's one of those things that can, it can stay valuable no matter what situation you're in and what part of the world you're in. So I think that's also one of the things. And as I mentioned, we've sort of seen these experiments happening. Like there's the Bitcoin beach in El Salvador, Costa Rica, excuse me, also has this like Bitcoin jungle thing that's happening, which is, sort of like you're living this nomadic life and, you hang around people who really like Bitcoin and the internet. And there's also been like a lot of talk about how Bitcoin sort of represents the early idea of the internet. People wanted to have the ability to transact across borders and not be limited by whatever geography they found themselves in. And so there's sort of like been this motivation for a lot of people who kind of found that sort of same utopia. And we also had this sort of, utopian idea with social media back in the day. We used to think that, oh, it's going to connect us, but maybe it hasn't really connected us as much as we thought it would. And there's always, this idea of utopias being corrupted as well. Excuse me. There's been a lot of pushback for a lot of people in especially like maxis, Bitcoin maxis sometimes. There's oftentimes like pushback against, more institutionalized versions of, companies like banks getting in on the bandwagon or IBM, coming up with its blockchain. So there's been a little bit of pushback. It's changing a lot more now. But, you have this sort of like, you have this idea of like you're building for a future in which, for example, this person was sort of talking about how, you have to be a true believer in the space. And that's also another part of the culture where you have to hodl and not really like, sort of sell the Bitcoin that you have. And you're sort of like preparing for that like future in the next few years, or I don't know how many years, but you basically create that world that is somewhat more equal, or they say that it's somewhat more equal, but you have, a society in which you don't really have government surveillance as much. So there's all of those themes that are also happening. And on the flip side, you also have people who are sort of saying, hey, I don't necessarily want to live in a world where Bitcoin is successful, because that represents a very dystopian future as well. This person was basically talking about how they actually like their bank to work, but they want more equal opportunities for everyone. So he sort of talks about like, if you're a sex worker and you want to transact value, you should be allowed to do that. So it's about basically having that freedom. And so that's sort of like what motivates him to continue to work on this space. One of the interesting things that is happening increasingly is sort of this, you might have come across the term network states. There's like these online imaginaries where people are gathering together on Discord, and then they're turning it into like real life societies. So this is a picture from my field work in Puerto Rico, and this was like right before the hurricane and stuff as well, where people were gathering together and they were building this house that was supposed to be like a retreat for other crypto folks in the space. There's also like, you have these almost like psychedelic dreamscapes that people are living on different islands right now. That's a part of the culture. It's not uniform, obviously, but there's a little bit of that too. So you imagine these like futures where, life is going to be kumbaya, basically. And there's also been experiments like, for instance, Zuzalu that happened, I think it was 2 years ago, maybe? Time goes by fast, but it might have been like last year, I think. And so they sort of set up this, it's almost like Burning Man, but it's sort of this city that they set up where they were trying to sort of have crypto as the main currency and stuff, and sort of creating these new forms of living, basically. And so in terms of potential utopias, obviously anonymity, decentralization, freedom of expression, freedom from government control, those are some of the ideas that, motivate a lot of the stuff that happens in the space. Obviously, there's a ton of, dystopias as well, where you have a lot of fraud, cybercrime, all of those things. A new creation of digital elites, basically, as well. So there's those things. And so some of the work that I do kind of contributes to different ideas that we have around technology and dystopian technologies or utopian technologies as well, and how we sort of manifest these like new worlds in which we are creating maybe a more equal world. Because like one of the things that does motivate a lot of people with Bitcoin is people wanted to be able to transact value across borders and not be limited by what part of the world they found themselves in. And I think like that's still very much like something that motivates a lot of people. And I will end right here. And I will also say it's interesting that like even Sam Altman of OpenAI, he has his own like crypto project. I think it's WorldCoin, where he's been scanning people's like irises, and you will basically have a proof of humanity of like whether or not you're human in the future that we live in with AI. So yeah, so that's it for me. Thank you so much for listening. Thank you for hanging around.
That was awesome. Thank you. I have so many questions, but I'll open it up to anyone else. I think I'll just start to what extent, like one thing I picked up is a lot of people you were interviewing were developers, or at least building tooling and things like that. So it's pretty uniform across, like, say, people who just own Bitcoin and hold it as an investment, and the people who are actually like building, the engineers and things like that. Or do you see that there's a bit of a divide?
So and this is one of the reasons why I kind of like the idea of the hive mind a lot more, because I don't think anyone in the space has similar motivations, because a lot of the developers, for instance, were very much like, it's a technology, it's an interesting idea that I want to work on. And so for them, money was not really a motivation. And especially like early on, and like when you like, there used to be people who would be on IRC and they would tip each other like 10 Bitcoin, and it wasn't really worth a lot. So there's been, I feel like a lot of every time that there's been like a bull run cycle, like the first one being in 2017, there's like a different sort of crop of people who kind of come in. And I noticed this in my field work as well, where it used to be like, just like people wearing, for instance, interesting clothes. And then I noticed this in my like field notes that I was taking. I was like, I'm noticing a lot more Deloitte, a lot more Oxford shoes, and so it's like there's been, Wall Street got interested, Silicon Valley got interested. So that's like every time there's almost been this sort of like washing up of the system every time there's been like, whenever there's a, like a downfall in the price, people kind of exit the system and stuff. So there's been like different kind of people who are coming and entering the ecosystem. And so there's not one motivation that really, sort of motivates them. It's more so everyone is kind of motivated, whatever, by, for example, a lot of people who have gotten in 2020, for instance, they were basically like, everything is about, monkey JPEGs. And so there's been like the Bored Apes and everything. So a lot of it is, they're not, I will say the people that I met early on, they were a lot more almost religious about Bitcoin versus, like they're also like, they hate terms like crypto and stuff. They're like, no, this is not, it's only Bitcoin, there will only be one ring to rule them all, kind of a thing. So yeah, so lots of diverse people in the space.
Lloyd?
Hi, Miriam. You are a grad. I really enjoyed your talk.
Very cool.
I have two questions for you. Number one, what's your favorite Bitcoin meme? And number two, what do you think about Bitcoin maximalism culture, specifically toxic maximalism culture? Do you think that will bring in the utopia, or like break it apart?
Very interesting question. So my favorite Bitcoin meme probably would be the Matrix ones that they have, like, the Neo, like those are, and it's also interesting. The memes are a very important part of the culture. They're almost like, I call them like ideological flashcards of like, because memes do work as like the morality police of the internet in many ways, where it's like, they tell you what behaviors are good or not. So there's the HODL meme. People celebrate like the Bitcoin Pizza Day, May 22nd. So that's like, it's a meme, but like, it's still something to celebrate. In terms of toxic culture, that's an interesting thing, because like, I feel like Bitcoin also has elements of, are there any Taylor Swift fans in the room, for instance? If not, then this is a good room. But you basically have, with Taylor Swift, you have these like Swifties. Beyonce has, the Bayhive or something. And you have this sort of like stan culture, which is basically stan means like stalker fan. And so with Bitcoin, some of that culture comes across in, the Bitcoin maxis. They're sort of like they stan Bitcoin and they kind of I think it's a complex issue because you do want as a brand, you do want some people willing to put their name on the line and kind of stand up for that brand and fight for it and like protect it because especially when it is a decentralized brand that's been undergoing a lot of crises, like you do need people to like kind of put their name on the basically say, hey, this is my flag that I'm gonna stand with and stuff. So I think there's that issue, but it does alienate a lot of people as well. Obviously, it's like you have a lot of people who started working on Ethereum were early Bitcoin folks, and so they kind of like it alienates people, and it doesn't always create a more inclusive space. So I think there's like it's a more complex issue. It's like, yeah. So I hope that answers your question.
Yes, thank you.
Welcome. And I think there's Sepide asked, how did you obtain, oh no, that's not for me. Gregory said observation community versus tribalism, or no, community tribalism versus ecosystem. Could it be as simple as distinguishing the ideologues as those focused on crypto while those actually building that is, yes, I agree with number one. In addition to dystopia, utopia, could you provide a vision of normal everyday life using it's a lot more it's obviously so the utopia dystopia is like one paper, it's not everything. Like there's a lot more, I think, like people who are in the space, they do obviously sort of like there's pockets of communities in Texas and other places where people do transact and live their lives with Bitcoin or Lightning Network or Ethereum. So you've got these like spaces where people are actually living those lives. It happens in Costa Rica, at the Costa Rica jungle. People are accepting Bitcoin as a currency, basically. So you've got like, I think at a certain point, people do want it to become a very normal fabric of society where people don't think about it as much. So I think that's definitely going to happen. And then your third question is, how does the recent, wasn't Roger Ver arrested recently or something? I remember something about that. But Roger Ver, sorry, who? Gregory. How does the recent book, I haven't read the recent book, impact that a broken Bitcoin SegWit was required for the Lightning Network, much in the crypto space, could quickly be swept away as utopian or dystopian. So it's interesting. Roger Ver, I actually met him at the Miami conference back in the day. And he was one time sort of seen as, like he was he was Bitcoin Jesus back in the day. And he's also become a controversial figure in this space. I haven't read the book, so I don't know what arguments he is making, but I do remember, I don't know, I came across something about something that was
I
happening.
think he had some tax problems recently, maybe in Spain.
Okay. Okay,
and
yeah,
then
that
he has
might be
the book about like kind of covering the fork between Bitcoin and Bitcoin.
That
Maybe
was
to some
considered
extent.
like
Exactly,
the
yeah.
Civil War. Like I think there's a lot of people who also like a lot of the developers, have really like one person kind of talked about it as PTSD from like that whole the factions that were happening during SegWit and the fights that were happening around then. But if I haven't read the book, so Gregory, I can't really answer the third question, but yeah.
Jeremy, if I may, just continue on that
Sure.
conversation. Yeah, because
Sorry.
I think you're right, Miriam. Good to meet you as well. I just want to follow up because it also connects with the previous conversation about the Lightning Network. But just in terms of you're kind of taking a sociological approach, you're doing a study of the different groups, and that's why I put at the top community versus ecosystem. And you actually just used that term in answering one of the other questions as well. But the forks do play a huge role, obviously, in the way that Bitcoin proceeded from 2017 onwards, and then it also Yeah,
I
and I don't know
totally
if you want.
agree. Like it definitely it created those like factions as well, right? And there's always, I think, like didn't they launch like Bitcoin XT? Like I think Roger Ver launched Bitcoin XT or something.
Well, then you have the current case in London too, which Craig Wright was. I think you're talking about BSD. He's lost that. We're waiting the judgment, and then the exchanges are being tried as well, because you have this whole issue is if you blocked off a system which was actually implementing the original version, right? Because Satoshi Nakamoto in the emails in 2010 was very specific. So this goes back to the previous presenter, very specific that there was an expectation that the block size limit would increase. He actually even gave a formula for doing that in terms of a rollout plan. And then you have that big break, and Mike Hearn and Gavin Andreessen being the one that receive sort of the keys to the kingdom, or at least you're the one leading the foundation or protecting the code. They were both big blockers, and it was a question of when, not if. So that to me is, because I'm a sociologist by background as well, so I'm not as much on the technical. That's why I was really pleased to have your presentation here and to see the way you approached it. And but to me, that's one of the big questions that remains to be solved, and we're seeing some of it in these cases come out. But yeah, I'd be glad to explore more. And the other question, I guess I didn't get anything out. Maybe because we're here in Canada. Is it how do you feel the reception in Canada in terms of one, where the government's at, and two, where the grassroots is at? Because I've talked to a lot of people in Canada who are not ready to uptake and on board. They don't trust it, or there's risks, or they fear the digital ID. And perhaps that's also why some of the leaders in the blockchain space in Canada are in the digital ID space, out in BC with the Truth Over IP Foundation and whatnot. So I don't know if you could comment on where Canada's at in your view, contrast to say years ago.
So your
when
question,
Ethereum
so your
was here.
question is, where is Canada at in terms of crypto in general?
Well, I'd say the blockchain specifically, and in terms of how prepared we are, we don't have the national programs that many other countries, Singapore, Australia, Nigeria, many other countries do. Um, you're part of this ecosystem in terms of where funding, and you can see some of that too. So I just wonder where, if you could come and give us some sort of update on where things are at, or how your feelings are about what Canada is doing and what it can do going forward.
I think I'm not a part of the government, so I don't really know. Like, I mean, I'm aware of like there's always, there's been a lot of curiosity, but also pushback against crypto and stuff. But I think it's going to be like one of the hard things with crypto is that it can shift very easily. For example, when China was banning Bitcoin, let's say. And it's also interesting that people if you were in China, you would say blockchain and not Bitcoin, because you kind of distance that thing. But, companies in the space kind of moved away to places like Singapore, or, they set up base in Hong Kong and stuff. And so it's been like, it's a transition. It's like, and we're seeing this like happen even in the United States, where, it's become almost unfortunately like a political debate when it should be more so focused on technology. And I think like the people who are involved in building the space, like, the developers especially, um, they don't really care as much about pushback. They're more so focused on like building what they think is an interesting technology and working, and they work really hard too. So yeah, so I think it's a thing that's evolving. So it's hard to give like definitive answers about like what's going to happen.
Thank you.
All right, thanks so much.
Yeah.
We'll move on, and yeah. Okay, so we had a break scheduled till 3. It's almost 3 now, but why don't we just maybe take like a 5-minute break? So we'll go to we'll start again at 5 after 3. Okay, it's 5 after. We'll get started again. So last but not least, we have a set of student talks, student postdoc talks. So these will be a little shorter, and they're again multidisciplinary. So Ella Coe is the first. She's at the University of Waterloo. She works on accounting and audit, and you can go ahead and try and share your screen.
Let me try to share my screen. Please let me know when you see it.
Okay, so I see your screen. You're a little quiet. I don't know if there's anything you can do from that end other than shout, but
Hello. Hi. Is this better?
yeah, it's doable. We can go with
Doable?
that. Yeah.
Okay, I'll try to talk a little louder then.
Okay, perfect. Thanks.
Okay. So good afternoon, everyone. My name is Ella Coy, and I'm a Master's of Accounting student at the University of Waterloo. And today I'm excited to share with you all a critical assessment of using blockchain for e-liabilities in the pencil supply chain as part of my master's thesis proposal. We'll start with a brief introduction of my project today, moving forward to a summary of literature reviews, to our approach for accounting for e-liabilities, and lastly, since the paper is still incomplete at the current stage, we'll talk about next steps for action items. My paper aims to critically assess Kaplan and Ramana's proposal published within their study Accounting for Climate Change back in 2021. They proposed to use blockchain for recording and monitoring e-liabilities, the total emissions from production. We have chosen to evaluate the concept through a pencil supply chain. We would like to further explore the advantages and the challenges of implementation of blockchain for recording e-liabilities, along with looking at the appropriateness and feasibility of a blockchain solution. So, why does it matter? Activity-based costing, also known as ABC, and blockchain solution for e-liabilities aims to enhance ESG reporting for accuracy and transparency. This is crucial as stakeholders increasingly base decisions on both financial and non-financial metrics driven by consumer demand and investor expectations, where we want consumers like us to make day-to-day purchases not only based on the price and quality of the product, but also the carbon footprint as well. Kaplan and Ramana have proposed to use blockchain and ABC method to account for e-liabilities in order to foster collaboration and secure data transfer. However, if blockchain isn't the appropriate or feasible solution, implementation could waste time and money. TradeLens, the only successful public blockchain-based supply chain network, ceased its operations in early 2023, mainly due to uncooperative network, which led the financial viability, which profitability is one of the most important factors for shareholders. We'll start with ESG for a summary of our literature review. ESG meaning environmental, social, and governance criteria to provide guidance to assess companies for socially conscious investors. And within the ESG criteria, environmental factors, particularly greenhouse gas emissions, hold significant weight due to their impact on global warming. Emissions are also one of the easiest to measure and one of the easiest to interpret when comparing to other social and governance factors like stakeholder relationship and corporate leadership practices. However, the current measurements methods like the GHG protocol face challenges of accuracy and reliability, which often leads to incomplete assessments. The GHG protocol separates emissions to scope 1, 2, and 3, meaning direct emissions from the companies, indirect emissions from electricities, and their upstream suppliers' emissions. Companies are only accountable for scope 1, incentivizing them to outsource the higher emission processes to greenwash reports. And double counting is also a major challenge, as one company's scope 2 emissions are another's scope 1. Therefore, maybe a single metric approach could resolve these issues. ABC offers a more precise approach to emissions accounting compared to the traditional methods. It allocates the cost based on the actual production usage, addressing the shortcomings of equal allocation across all products. The graph presents and illustrates 7 direct materials purchased by the pencil manufacturer: brass, eraser, pencil, lead, wood, paint, glue, and cardboard. And each material may have multiple suppliers upstream. The manufacturer assembles and the components and packages 5 pencils per cardboard box before selling to retailers like Walmart. A pencil manufacturer calculates the cost for 1,000 pencils, so all of the costs above will be $464 for the materials and other costs. And assuming no markup, this cost transfers to Walmart, then to the consumers. For each manufacturer and Walmart, the $400 of cost outflow balances with the $400 of revenue inflow, netting zero. Customers paid $464 for 1,000 pencils without the revenue inflow as the end consumers. Woodco specializes in harvesting, slicing, and delivering high-quality wood for pencil production. They produce 1,000 kilograms of wood and sold 10 kilograms to a pencil manufacturing co. totaling $100. ABC accounts for the financial impact of raw material purchases involving an asset exchange of materials for cash. And in today's environmentally conscious society, calculating emissions throughout the pencil supply chain is necessary, extending beyond the financial metrics alone. To account for emissions using cost accounting, Kaplan and Romana proposed the concept of e-liabilities, which is environment liabilities. E-liabilities represents the emissions for which an organization and its suppliers are responsible for, and e-assets are the positive environmental impacts that a company makes, such as carbon offsets, trees, plantings, and more. So let's apply the cost accounting method using e-liabilities to our pencil production example. We use kilograms per carbon dioxide equivalent as the unit of measurement. The manufacturing company purchased 6 direct material. Along with the transfer of these materials, the associated emissions up to that point are also transferred to the pencil manufacturer. And following ABC principles, other costs have also been allocated to labor and electricity as well. In addition, since 5 pencils share 1 cardboard box, the emissions associated with the production of cardboard boxes should be distributed accordingly as well, and therefore the total emissions to produce 1,000 pencils are 102. Emissions can be decreased by sustainability initiatives or by selling items to customers. And in this case, we'll transfer the emissions to Walmart. And Walmart's perspective, they acquired 102 emissions from us and will reduce their e-liabilities through carbon offsets or by selling the pencils to end consumers. Each pencil sold will carry 0.1 emissions displayed on the price tag, so consumers can consider their carbon footprint along with the price and quality when they're choosing which pencil to buy. Kaplan and Romana have suggested the use of blockchain technology to enhance immutability and build trust in the cost accounting and e-liability system. Some advantages to blockchain include security of data, encouragement of collaborative environments between participants, and immutability, where naturally enhances trust and constitutes reliable data to transfer e-liabilities accounting. However, blockchain isn't suitable for every situation. Its deployment must align with the needs of the organization when determined as appropriate. There's also permission versus permissionless blockchain adoption. There are 5 situations for when using blockchain is more advantageous over a traditional database. To establish trust when participants do not fully trust one another, the need for immutability for their ledger, where modifications will need to be detected, transactions to be reviewed by proof of work or proof of stake, foster a collaboration between participants, and lastly, the need for transparent and auditable data. A decision tree has been created to assist organizations in determining the appropriateness of blockchain solution for their specific needs. The decision tree can lead up to 4 possible outcomes. 1, they do not need a blockchain solution. A traditional database is sufficient. 2, a permissionless blockchain where they do not trust anybody and the proof of work will be needed. 3, a permissioned public blockchain where they know all of the members, but all of the members are from different organizations and proof of authority will be needed. And 4, permissioned private blockchain where all of the members likely work in the same organization, but a proof of authority is also needed. Before implementing blockchain, Feasibility must be assessed through a cost-benefit analysis, and challenges include resource allocation, participant agreement, and technological readiness as seen in previous industry failures like trade lines. So looking at our approach, we'll start with the supply chain of a pencil. Combining all of the concepts above, each of the supplier's emissions data will flow to the pencil manufacturing co, then to retail co, then eventually presenting itself to carbon footprint to the end consumers. We've gone through each decision criteria and have determined that a permissioned public blockchain is deemed as appropriate, ensuring transparency and security in the emissions reporting. Some of the key factors can include trust, where all 14 participants currently may not trust one another, and some suppliers who are engaging for the first time naturally lacks trust. 2, data manipulation. There are incentives for each company to understate their own emissions for a greener report. And 3, consensus mechanism. After a transaction has been posted, various participants will need to approve the transaction unanimously before updating each participant's ledger. Now that we've determined that it's appropriate for pencil supply chain to be implementing a blockchain solution, we'll need to determine its feasibility. Feasibility hinges on overcoming common implementation hurdles like generating network effects, managing technological complexity, and integrating blockchain with the existing system. And these factors can influence the success and the sustainability of a blockchain adoption. While our pencil supply chain involves over 14 companies with no concerns over the lack of users, the lack of user cooperation remains a significant challenge. Companies are reluctant to share emissions data due to the competitive concerns and potential reputation damage from disclosing high pollution levels. Even if the companies do want to disclose the data to their consumers, they would not want this information to be exposed to their competitors, and therefore implementation may be both advantageous and disadvantageous to the reporting company. And some companies, especially smaller suppliers, resist adopting new technology. They prefer their current data entry methods and are unwilling to allocate additional resources for blockchain implementation. And blockchain alone actually isn't sufficient for tracking emissions data. Companies may find managing multiple software systems to be burdensome, especially for voluntary reporting, where blockchain will need to be integrated with their current ERP system, serving as a value-adding process to introduce trust, immutability, and the avoid of single point of failure. In addition, an Internet of Things sensor may also be needed to actually capture real-life emissions data. Since my paper is still in progress, I wanted to talk about some next steps or some action plans after the presentation. We would need to gather emissions data through obtaining industry average emissions data for real-world supply chain of the production of pencil. 2, to build a relational database to organize the emissions data. 3, to develop an accounting procedure through ABC methodology. And 4, creation of simulation of blockchain for the pencil supply chain for its appropriateness and feasibility. And in conclusion, while blockchain offers significant benefits for e-liabilities accounting, its implementation requires careful consideration of organizational readiness and industry dynamics. And thank you so much for listening to our presentation. We're now opening the floor to any questions.
Great, thanks. So questions for Ella? I'll start with one. Let's say we had one of these systems in place. Who do you see would actually do the audit? Do you think it would be like a private firm that the company would hire, or is it a government agency, kind of maybe like ingredients on food are I presumably inspected to make sure they're truthful and accurate?
Since we're proposing basically an e-liabilities accounting method, I would still think the current accounting firms, for example, the Big Four, would be responsible for audit, or any mid-size or smaller size firm, depending on the company's needs as well. Since the Big Four currently do offer some ESG audits, but I believe currently one of the challenges is how do you perform an audit when you're using industry average, it's really hard to find whether or not if the information is actually accurate. That's why auditing and accounting it has been hard.
Understood. So because there's so many third parties involved, you would have to cross check all the information across all the manufacturers of the ingredients. Okay, there's a question in chat too, or if you want to just unmute and ask it.
My question was, are there any other fields where you'd like to see blockchains used to improve accounting?
That's a very good question, actually. I think currently, definitely something like ESG or like, starting with ESG or actually accounting would be the best one, since first I'm most familiar in that. And then also other fields, I would say first, so I mentioned before that we started with the environmental factors because it's the easiest to measure. So maybe moving into social and governance, and actually, for example, if the government promised us, okay, we have reduced something by 10%, and actually using blockchain to actually track where that 10% came from would be better for transparency.
Cool, thank you.
Okay, Gregory.
Yeah, hello. I'm not sure if it's echoing. I had to change devices here so I can say hello as
Sounds
well.
clear.
Great. Yeah, so I wanted to ask you about triple entry accounting and if it comes into your research and focus there in the blockchain space. Because that's what got me really interested when I read the paper by Ian Grigg. I put the question and then not too long ago I discovered, and I people I've spoken with didn't know about it, but to me it's fascinating. I'm not an accountant, but a sociologist by training. But Fyodor Ozersky actually was the earlier inventor and innovator of this, and Yuji Ijiri, who is often credited as the inventor of triple entry, followed on over 100 years later. But there's some fascinating ideas, and I think that it'll fit into your research because I think you're going in the right direction with this. We've got a pencil. We're looking at the ecosystem of all the things that are going in, the debits and the credits, but then what is the public ledger? And it can include some of these concepts, and I think Ian Grigg didn't have it all right as well, but I think it would be a good complement to what you're doing there and to include it.
Jeremy, may I answer the question
Yes.
instead
Yeah,
of
go ahead. So Theo's her supervisor.
Gregory, there are several papers that have been written by accounting professors about triple entry accounting. The Ijiri is not relevant for what we're talking about. It's completely different definition of triple entry accounting, but the Ian Grigg version is relevant. And if I remember correctly, the name of the professor is Chow from a university in Australia. I've used in a lot of reviews. He's written an excellent paper about triple entry accounting and how it connects with blockchain. For what Ella is doing right now, I don't think it's so important. At least we didn't consider this angle yet. Thank you.
If they have an annual event, I'm not sure if you're aware of it, but there's a triple entry accounting. It was in Malta, I think, last year. There's a Greek professor, Kostas, Sigantos, I think if it's the event. But it might be an interesting community to see, sort of bounce ideas off each other's and see how it might be relevant, because I think you've got some interesting ideas and some of this could supplement and it could kind of add extra layers that really would help the public understand what the accounting is doing, because I think it's such an important field for overall. I mean, Victoria in the information library sciences and archival sciences, that's a very interesting field too. That's different than sort of computer science, let's say, or business, making business models. So for me, that was a fascinating presentation and what you can do with it. And we're going to go, Ella, I think it's great possibilities.
Okay, let's thank Ella again. I think she has to run off to class anyways. And so thank you. Okay, we'll move on. So next we have Preston Haffey from Calgary. I think his second time maybe presenting here, if my memory serves me correct.
Yeah. Yes, I'm a bit under the weather, so I'm just gonna keep my camera off and then
No worries.
but I'll start sharing my. Yeah, so my name's Preston Haffey, and I'm going to present a work that I worked as part of a team with Mamoun Nabi, Sepida Avize, Rehana Safavinani, which is our supervisor, and then Mark Neppers from TELUS as well. So this is work that we presented in the Hawaii International Conference on Security Systems. And so our work is titled SIG Bridge, and it's a cross-chain bridge for permission blockchains and its application to decentralized access control. So just a review of the two main types of blockchains. There's permissionless and permissioned blockchains. So in permissionless, anyone can join and participate in the network, and parties have to expend resources to participate in the network as part of the consensus algorithm. So types of consensus for permissionless are the proof of work, where you're spending computational resources, or proof of stake, where your weight in the system, it corresponds to the value you have, so your stake in the system. And it's easy to join, but there's poor performance, and scalability and privacy are challenges in permissionless blockchains. In permission blockchains, the ecosystem is like restricted, so only registered entities can join and participate in the network, and parties enroll with their identities that are hard coded in the software, or they're updated as new people can register. Their identities are included, but only people with registered identities can participate in the network. And there's types of consensus for this is the BBFD and proof of authority. And the benefits of permission blockchains is that there's higher performance because each node is having to spend less computational work, and it's easier to scale, and privacy is easier to achieve as well. So what our work is on a cross-chain bridge. So I listened to this podcast a while ago where the host talked about blockchains, and he said they weren't very interesting because they're basically Git, and that was invented like in the 70s. And the blockchain data structure, the way we think about it, is similar to Git, where we have a state and then a hash of the previous state included in that state that provides like a sequential sequence of states. But that kind of misses the main point, where, in blockchain, you have a whole bunch of nodes that potentially don't trust each other, and they all maintain their own copy of this ledger, and they all come to an agreement somehow, even though they don't trust each other, on what the state of that chain looks like. And so when you have one blockchain, the way that all the nodes agree is through running the consensus algorithm. But if I want to communicate something about the state in this blockchain to someone outside of the blockchain, who isn't able to participate in the consensus algorithm, it becomes very challenging, because now that root of the trust that's generated through consensus, the person outside of the chain I'm communicating to, they're not involved in that consensus mechanism. So what cross-chain bridges do is, if we want to have applications that run on data stored in multiple blockchains, we have to find a way to bridge the data from one blockchain to another, so that if I'm an application running in the blockchain 2, and I rely on some data in blockchain 1, I want to have the same confidence on this data in blockchain 1 as I do in my native blockchain, but without having to, just be a node in blockchain 1 and run the consensus algorithm. So essentially, if we want to be a bit more precise, the cross-chain bridge, it provides evidence to applications in the blockchain 2 that a specific event occurred in blockchain 1, and vice versa. So examples of these specific events would be transactions of data, or asset transfers, and transactions of content being created, and or function calls being executed in one blockchain. And to have a cross-chain bridge, the requirements are correctness. So the blockchain 2 receives a correct view of blockchain 1, and liveliness. So the data in blockchain 1 is always available in blockchain 2. And so some existing approaches, use an honest majority committee, Ronin, Axelar, Polynetwork, Wormhole, or incentivized bridges, Near Rainbow, Nomad, and then light client-based approaches, which are ZK Bridge, Cosmos, and Polkadot. The disadvantages are of these existing approaches is that they're poor performance. So doing like an honest majority committee, you have to have nodes running in multiple blockchains, running multiple consensus algorithms, or there's a reliance on central party. So you're putting a lot more trust in the bridge than you would in one of your specific blockchains. And the designing these things correctly is very complicated. And so our work is to take the approach of ZK Bridge, which is for a permissionless blockchain, and that uses zero knowledge proofs, and to apply it to the permissionless, our permission blockchain. So I'll just give a bit of an overview of the ZK Bridge approach first. So if we have one application in blockchain 1, we call it the sender chain, and another application in blockchain 2, ZK Bridge lets us reflect the states of the application 1 correctly and timely in the application 2. And we use cryptographic assumptions. So security here relies on the zero knowledge proof rather than an external committee that we assume behaves correctly and that we trust. And how it works is that we run a relay network that runs a light client. Just to be, this can work in both directions, but just for concreteness, we'll refer to the blockchain 1 as the sender chain, and then blockchain 2 is the receiver chain. So the relay, it runs a light node in the blockchain 1, and light nodes they're like nodes in a blockchain network, but they don't store the entire contents of the ledger. They just store the block headers. And with a block header, if I receive a transaction, I can check to see if that transaction is in the blockchain using information in the block header. So we run a light client on blockchain 1. And the light client communicates with a smart contract called an updater contract on blockchain 2. So the light client 1 sends block headers and a ZK snark proof that this block header actually belongs in blockchain 1 to the updater contract on blockchain 2. And the updater contract runs a light client protocol that keeps track of the block headers and events in blockchain 1, and then verifies the block headers and the proofs that it receives from the light node. So our work is, well, first we start with an observation that in the permission setting, on-chain computation is not as costly as it is in the permissionless, and the consensus logic is simpler. So instead of running a proof of work, we could use just a threshold of signatures. So if there's 10 consensus nodes, I only need 8 signatures from these 10. And then I'll know that this information is valid in the blockchain. So our SIG bridge adapts the ZK bridge from the permissionless to the permission blockchain setting. And it uses the signature of the consensus protocol of the sender chain for block header verification instead of zero knowledge proofs. So we kind of remove the expensive computation of verifying the zero knowledge proofs, and we replace this with signature verifications. And we use a probabilistic verification algorithm. So if we receive a block that's been endorsed, it has like 10 signatures, and the threshold is 8, we'll just randomly pick 8 of those signatures. And as long as all 8 of those signatures are valid, then the blockchain 2 will accept that information. And we apply this SIG bridge to a resource sharing application across 2 permissioned blockchains, which I'll describe later. So the SIG bridge, we developed kind of this architecture for SIG bridge, and we use a 4-layer architecture, which is kind of an abstraction of how the architecture in ZK Bridge works. So we have a message passing layer. So we need to be able to kind of physically pass messages from one blockchain to another. And we have a relay network of nodes that will help us pass these messages, and a relay manager that handles the registration of these relay nodes. And then a consensus layer, which focuses on the consensus protocols of the blockchains. And then a cross-chain synchronization layer, which makes sure that the state of the blockchain 1 is synchronized with the state of blockchain 2, so that blockchain 2 has a live view of what the state of blockchain 1 is. And then an application layer where we can build applications that use data from both blockchains. And so we have a SIG bridge framework that reflects the state of the application. AC here is for application contract. So the states of application contract 1 are correctly and timely sent to the application contract on blockchain 2. And ours, like the ZK bridge, we use cryptographic assumptions where instead of zero knowledge proofs, we rely on signatures of consensus. And our approach is application agnostic. So we can build any application on top of this bridge. The functioning of the bridge isn't specific to a certain type of application. And so we have the three main types of entities. So there's the relay network. So this is a set of registered nodes, excuse me, that receive data and then a signature of consensus. And it applies a transformation onto the signature of consensus, which could be just the identity function or a threshold function. But this transfers the consensus information from blockchain 1 into a format that the contract on blockchain 2 can verify. And so the relay network, it will receive transactions that happen in the blockchain 1 and forward these and the necessary information to the updater contract in blockchain 2. And our updater contract, it collects the block headers and proofs, applies the transformation V to the received block header information so that it could be verified. And then the application, smart contracts, a third type of entity, determines which information should be passed to the other chain through the relayers. Because the ZK bridge, we're not sending the entire state of blockchain 1 to help with efficiency. It's just when if the application 2, the AC2, needs some data, this application smart contract decides which data actually needs to be sent from blockchain 1 to blockchain 2. So this helps keep our solution efficient, that we're not transferring all the state constantly from one blockchain to the other. And so an important part of this is a block header synchronization. So we have a setup phase for our SIG bridge where the system administrator of the blockchain 2 initializes the updater contract. And the relay nodes are registered into the relay network where each node, they generate a public and private key pair and receive a public key certificate for their public key. And this is managed by like an entity or a trusted process that both blockchains trust. And then a block header synchronization, the relayers, when a new block is added to blockchain 1, the relayers receive the block header and applies the transformation T, and then signs the block header and sends it with its public key certificate to the updater contract. And the updater contract validates the block header based on the transformation V. So once it receives the block header, it checks the proof that this is a valid block header from blockchain 1. And if that proof is valid, it stores the block header here in the blockchain 2. So you can kind of see in this diagram, the BC1 blockchain, the blue part here, this is like the list of all the transactions, and the orange here is the block header. So blockchain 2, if it wants to verify a transaction has occurred in blockchain 1, it doesn't need to store all of this information. It just needs to store the block headers here, so that way later when I send a transaction to blockchain 2, it can use the information in the header to verify that that transaction actually occurred in blockchain 1. And so we use our ZK, the SIG bridge to develop a cross-chain resource sharing application. And this is based on some previous work where we did this resource sharing based on in a single blockchain ecosystem. To begin with, the idea of a resource sharing, you have a user who wants to offer a good or a service, but I want to specify some conditions on the access. Let's say I have a movie that I want to make available, but I only want to make it in certain regions. I could have a policy that checks, make sure that only people from Europe or Asia are able to watch this movie. And so users will have attributes that will be checked against the resources access policy. And if the user's attributes satisfy that policy, the user gains access. And so a kind of a simple way to do this would have a service provider, like a telecommunication company, host this service. So resource owners can register their resources, and then resource requesters can request access, and the service provider, they do the checking of attributes against the policies and then give access to the requester if their policy is satisfied. And so previous work by Mooney and Vijay use smart contracts to offload the trust assumption that we have on this service provider here. So in this way, we have this access policy being executed on a blockchain, and this helps reduce the trust that we have on our service provider. And what we're looking at is, how do we provide this? But if we have a resource owner,
Seems we maybe lost Preston. Just give him a minute to reconnect. If anyone has questions for him, by the way, you could drop them in the chat now. By the way, so the next speaker is Kusha. Are you online? I don't see a screen name that corresponds to your name, but you might have it under a different name. Okay, well, skip Preston maybe 30 more seconds, and then maybe we'll just move on to the next talks, and then I'll chat with him and see if he wants to finish his slides up in a bit. So Kusha, I don't see you. Oh yeah, okay, so Preston's back.
sorry,
No worries, no worries.
my cord is frayed, so I needed a new one.
Okay, we're almost at time anyway, so maybe you could just wrap up quick, and then we'll move on.
Perfect.
With or without slides, up to you.
Yeah, that's sorry. That was the one of the last slides that I had anyway. So, and yeah, so the last thing I'll just mention is that we implemented this using 2 private Ethereum networks, and then ran some experiments to check the feasibility of our results. And basically, we were measuring the part of the security for our system is based on this probabilistic checking. And the more signatures you check, the higher security you have, the less chance there's some forged signatures. And from the relay network, because in our security model, we want to have a relay network where we could trust almost none of them, but as long as there's one honest node in the relay network, we still have some confidence in the system.
Got it. And are the signatures recorded on blockchain 1, or are they just submitted directly to the bridge and not on chain?
They're part of the consensus of blockchain one. So they're just they're on the blockchain one as the normal blockchain data, and then they're gathered by the relay nodes and sent to blockchain too.
So you can't choose the signature scheme because, like, you could choose to use BLS, for example, and then you could aggregate your signatures and just do one check for all of them. But I guess you don't have. It's up to the blockchain. Whatever the blockchain uses, that's what you're stuck with.
Yeah, exactly. Yeah, because you want to be. Yeah, that's exactly it.
Got it. Got it. Okay. Thanks, Preston, and we'll move on. Okay. So Kusha, are you online in the call? Not sure where the breakdown was there. We'll just skip over you for now, and then if you come back, we'll certainly give you your time. Ami Reza, you're also at Manitoba, and I also don't see you. Okay, so let's go to Trinh Nguyen, who's helped organize BTS maybe a couple years ago when it was at UBC, did a lot of work on it. And so we're happy to have you back. And yeah, why don't you go ahead?
Thank you very much, Jeremy. So first, maybe let me start sharing my screen. Share screen. Can everybody see my my PowerPoint?
Yeah, we see everything looks good.
Okay, let me put it to full screen. Oh, there we go. Okay, thank you everybody for staying into this very last minute. And my name is Trinh Nguyen. Today I will present my PhD research entitled Exploring Information Governance in Decentralized Ecosystems. And a little bit about me. I'm in my third year PhD study at the University of British Columbia at the School of Information. And currently I'm a PhD candidate in the department. The first time I know about blockchain technology symposium was like 3 years ago when I support in the organizing team, and I'm very happy to come back this time as a presenter. So in today's presentation, I will briefly go through the problem, the purpose of the study, the significance of it, overview of the literature very briefly, and then the methodology that I will be using for my research, then discussing the research limitations and future direction. I am currently conducting this research. So any feedback or suggestion from the team will be greatly appreciated. For the problem, this has been the motivation and my interest in the last many years. That is, recently, a lot of high-profile blockchain projects didn't harvest very positive result. For example, TradeLens has continued operations, and it has announced it in by the end of 2022, and officially closes operation early last year. Then also some other high-profile project like the Food Trust of Walmart and IBM also start diminishing its public presence. So and also other warning about other blockchain project like IBM seems to start reducing its blockchain presence as well. However, not all things are that bleak. For example, blockchain is still touted to be a very good technology to enhance the supply chain transparency and traceability. And now in the space, we don't only see the private sector or the blockchain enthusiasts, but we see bigger players, including the government, joining the blockchain experiment. For example, the British Columbia government is using blockchain technology to enable efficient and safe interactions between government agencies, business, and organizations. And especially now they implementing the use case in critical minerals mining. So this poses a question: why are some blockchain systems more successful than others? And I will investigate this question using information studies, theories, and based on information studies, I study this issue from the informational perspective. And from this study, I hope that it will advance information control theories by examining them in the new context that weren't available when these theories first emerged in about 1986, 1989. And also, I will connect recent information governance discourse with its theoretical root, which currently has been overlooked in the more practically oriented information and record management literature, and also identify the information-related success factors for the current and future blockchain projects, and hopefully to develop a comprehensive information governance framework for decentralized system. So briefly look at the literature. I see that in the blockchain governance literature, the dominant paradigm now focus on the social and the technical aspect of blockchain. As we have seen in the whole of like most of the presentation today, the technical aspect have a lot of attention and in-depth research from different disciplines, especially in computer science, mathematics. But and the social science also trigger a lot of interest. For example, the very interesting study of the utopian dystopian that we have just recently listened from Marion, which I think that's a fantastic study. However, another aspect of blockchain that haven't been focused substantially, that is the informational part of blockchain. And this is not only the information which is the data that is recorded in the lecture, but this is also the information exchange, the information governance that happen in the off-chain management layer. So therefore, from that literature, then if we go have a looking deeper at the information principles that is embraced by blockchain and compare with the traditional information governance principle, we see some overlapping here, including both systems embrace transparency, integrity, security, availability, and retention of the information. As we have seen, this is very clearly in the first blockchain, the Bitcoin blockchain. But there are also some significant difference. For example, traditional information governance principle really enforce accountability based on a centralized, trusted party, the compliance with the existing regulatory framework, and the disposition of the information. On the other hand, information-related issues in blockchain embrace the principle of resilience. Now we have a network of decentralized nodes. Each one has its own lecture, a copy of the lecture. And then the network will ensure that the whole network will stay resilient with minimized chance of a single point of attack. So given this difference, we can see that there are mismatches between information governance in traditional paradigm and decentralized paradigm. So how do I go about to research this? I will use a combination of case study and comparative method. For case study, it will provide a rich description and deep analysis of singular case. And in this case, I will use two cases. The first one is the EMDT, which is the Energy, Mines, and Digital Trust project that is implemented by the BC government. And currently, I'm a research intern in the project. The second case will be a permissionless blockchain used by the Open Forest protocol. And I have been contacting with the team, and they quite open for research in information governance in the system. So these two case studies will provide a really in-depth discovery of the information governance in these projects. And for data collection, I will use observation, which means that I will participate in all of the meetings that this project team have, and then have in-depth interview with the participants in those projects, and also document research. Then I will compare these two cases to pattern trace between these cases and understand the success factors that this case have. For analysis, I will use hermeneutic phenomenology, which emphasizes the understanding of human experience in the living world. And the living world here is their project, the decentralized project that they engaged in to transform the sector that they have been working at. And it also requires the researcher to live in the research context, which is why I use observation and the case embedded in its study. And I believe that this combination will provide offers a profound and holistic understanding of how stakeholders perceive and experience the complexities of the information governance in their project. Of course, even though I believe that the method is very suitable and feasible to do for my my PhD research, I have to acknowledge that they have they have some limitation. So first, because this is feasible, so the study, my 3-4 years PhD study can only do in-depth analysis of 2 cases, and both cases can be considered as relatively more successful than others. For example, trade lands or food trusts that I have mentioned before. And I try to mitigate that by clarifying the research expectations and validity upfront. And also, I will have a bit limited in-person context during the fieldwork, even though I have been participating in their research. In the project team, basically work fully remote, but I surmise that having more in-person contact would actually increase my rapport with the team. And for this, I will have prolonged engagement in the project, which I hope will reduce this limitation. And I really wish to have more research in the future of both successful and especially unsuccessful cases. And that is the end of my presentation. Thank you very much for your attention. Welcome all of the questions, critiques, and suggestions.
Great, thank you. Any questions or suggestions? So I'll ask one. If you go back a few slides to your Venn diagram.
Oh, yeah.
Yeah, that one. So you have resilience on the one, like on the blockchain side, right?
Yeah.
Is that really not like something that's considered, or would it be buried underneath one of the other kind of properties, or like it seems odd that it's sort of not considered in GARP.
Oh, yeah, thank you. Thank you for your great question. I would say like the differences, even though it's in this diagram, it seems to be very disparate and totally like disconnect between the decentralized or centralized. I would say it's actually implied in each of the paradigm, but whether it is the priority or not is like the question here. For example, in traditional governance system, the resilience, I think it is embedded in like accountability, like in some way that the key person or organization in charge need to ensure that information is resilient enough to continue the operation of the given organization, but it is not explicitly mentioned. We kind of assume and imply that in the current governance system. And for blockchain, I wouldn't say it is non-accountable, because like now the accountability is reside in every single individual, but there is not like a centralized trusted party to ensure the accountability of the whole system. So they are still accountable in a new way. But I would say like resilience is more explicitly focused and prioritized here.
Got it. Makes a lot of sense. Okay, all right. Thanks again. And we'll move on to the next speaker. So Kusha Korasani is at University of Manitoba. And yeah, take it away.
Okay, so hi everyone. And first of all, sorry for the inconvenience because I had this connection problem, but thank God I actually overcame that. Okay, so let's share my screen here. Okay. All right. Okay, so I guess you can see my screen now.
Yeah, looks good.
Perfect. Okay, so today I'm gonna present you my project, Automated Gateways through Smart Contracts, which is developed in the TCDT lab of University of Manitoba under the mentorship program of Hyperledger Foundation. So this program was basically was funded by Linux Foundation for developing a blockchain interoperability solution. So first things first, our team consists of Dr. Saror Rohani, Assistant Professor of University of Manitoba, who is my supervisor, and also Mr. Wahid Pouhaidari, who is my supervisor for this specific project. And the next one is Mr. Rui Pan, who again supervised me in the Hyperledger Foundation. And this is me, Kusha Khorasani. I'm a master's student of University of Manitoba, and I'm conducting research about blockchain interoperability. And I was a mentee in Hyperledger Fabric mentorship program. So first of all, about interoperability. Well, interoperability refers to the ability of blockchains to communicate with each other. And nowadays we are living in a Web3 community, which is full of different blockchain platforms. So we have like Ethereum, Stellar, or Hyperledger Fabric, but unfortunately they are acting in data or service silos. So it means that although they have a huge deal of actually distribution, but they do not have some capability for communicate with each other. So interoperability is a way that we try to connect these different blockchains. And we try to do that in three main aspects. The first is token swap, which we basically swap tokens between two platforms. The next one is token bridges, which means that actually we exchange tokens between two platforms. And the last one is contract call, which involves a smart contract on a source chain, calling a smart contract deployed on the destination chain. And through that, we can share the services and we can share the data. And that's the contract call solution is what I have implemented. So why interoperability matters? Well, obviously, we need to make these different platforms talk with each other and communicate with each other. We can have even more distributed systems, and we can benefit from different financial capability of different blockchains. So the problem that I try to actually address is based on two different categories. The first one is the various technologies. So for blockchain interoperability, we already have some solutions. So the idea is not novel. We have Axelar, we have Hyperledger Cacti, we have Weaver, Polkadot, Cosmos, many things. The problem is it's hard to choose between them because each of them have different technologies and different designs. The nature of IT products is ever changing. So sometimes you choose one of them for your technology, but it's gonna change in like 3-4 years, and you need to just again change your platform. And also they are all created and maintained by the other companies, and well, they might change. There might be miscontinuation of the service. The other problem is about cost. So when you have a solution and you want to use other interoperability solutions, you have to learn a new technology. You have to check the compatibility between different products, and you have to code to connect your platform to the bridges. And also sometimes you have to even hire more people who are familiar with these bridges. All in all, it's gonna be really costly. So we talked about solutions. We talked about problems. So now we need to provide some solutions. Let's start with defining a good solution. So a good solution, obviously, is the one that doesn't have the problems that I just mentioned. And also, it should let the owner of the blockchain decide for the policy. It should give the owners, 100% power to change the policies or control the policies. And also, owners should have access to different sections of interoperability solutions. And also it should be self-reliant as much as possible. It means that we need for creating an interoperability between two different blockchains, we need to use the capabilities that our host blockchain already has instead of just using another bridge. So we need to minimize the need for using third-party solutions and also learn a new tech stack or facing new challenges. And also it should be efficient in regard with time and cost. So based on this definition, we come up with our solution, which is automated gateways. So automated gateways consists of two different parts. The first part is the smart contracts, as you can see here. And the second part is a relay that we published as a as a Go module. It's basically a library, and we just need to add it to your code. So let's dive deeper in our solution. So regarding the relay, let me show you again. Regarding the relay, we have two different parts. One part is network neutral. The other part is network specific part. Network neutral part just connect different blockchains regardless of the host blockchain. But network specific part, it is the part that actually works with our host blockchain, and it has the features to support our specific blockchain. So the network neutral part is, as I said, making connection between two blockchains. The main part of authentication between the different blockchains is happening here, and it uses gRPC at its core. And the messages between two different blockchains are created here, and they are sent or received here. The other part is the network specific part. So here we create the network specific part creates and manages connection between relay and blockchain. It gets the messages from network neutral part and translates it to the protocol that blockchain can understand. And for each supported blockchain, this section implemented based on the SDK provided by that blockchain. So for example, right now we have in our GitHub, we support Hyperledger Fabric, and now we are developing support for Ethereum. So the next part is the smart contracts, and we have three different smart contracts. The first one is Accessible Network Manager. It keeps the data of blockchain networks that we have access to, and the data we keep here is the network name, the IP, the address. By address, I mean the URL, and the company name and accessible network ID. It basically supports different methods in this smart contract, which handles the create, update, remove, and query the information about accessible networks. The second smart contract is Permitted Network Manager. It controls the data and the level of access of an outsider blockchain networks. So it basically controls the authorization of outsider blockchains. Here we just register the information of the blockchain networks that have access to our services. So it contains network name, it contains IP address, the URL address, and company name, and permitted network ID. And it has the same methods there. It basically the fraud methods. The last one is Permitted Method Manager. Well, basically, the Permitted Method Manager is the next level of authorization. So in the Permitted Networks Manager, we dedicate which networks have access to our host blockchain. Here, we dedicate the specific methods that each permitted network can call or can invoke. So here we just define the permitted method IDs, the method name, the name of the chain code or smart contract, the name of the channel that our smart contract is actually deployed on, the method inputs and method outputs. And basically it has the CRUD as well. Okay. So let's dive deeper in the architecture part of the relay. So in the relay, we have different parts. We have mediator, we have the chain connector or gRPC part, we have the on-chain part, we have the CLI, we have config file, and also we have the user code. Mediator is the heart of our system, and it basically connects different sections of the relay to each other. It connects user code or outside their blockchains to our blockchain. So it means that by sitting in the middle, it can connect our gRPC APIs to the on-chain part, and through that, it can connect different blockchain. Also, it provides APIs for calling by, for the user's code. So basically, a user just use our library, and it just calls our API there, and it's basically communicating with the mediator. And also, it manages the access control and interoperability, and it connects the CLI or user code to the gRPC component as well. So basically, it connects different parts to each other. Inside the mediator, we use factory design pattern to connect different blockchains, and we have 3 interfaces. And based on those interfaces, we can connect different blockchains with the minimal changes. So we just had this basis, and we just extend the basis for connecting different blockchains. And for each blockchain network connected to our module, we should just implement these interfaces, and then bam, we can just connect the different host blockchains. So here you can see a process fellow and outsider component just send a request to the factory pattern, and it's just use the implementation of the interface based on the host blockchain. It can be like Hyperledger Fabric, it can be Ethereum, and then it can just become connected to our host blockchain. And here is a more high-level images that, as you can see, we have the CLI is command line interface, or the user's code, which can connect to our IOP mediator based on the APIs that we have already developed. The next part is the on-chain component. Well, here we just connect our mediator to the blockchain, to our host blockchain, and also here we have this infrastructure for invocation of the policy management smart contracts, which were permitted method manager, permitted network manager, or accessible network manager. The next part is the gRPC part, which is our component in which we can connect different blockchains to each other. And here, we have a gRPC as our core, and it handles the authentication based on the certification, based on the certificate-based authentication. So here, the owner of the host blockchain needs to issue some certificates for the permitted networks, and using this certificate, they can connect to actually our solution. The next component is the CLI part, and just to make long story short, we have some command line interface that user, which is a non-developer or non-tech user, can communicate with the interoperability module just to manage its blockchain. And the last part here is our configuration file. It is basically a YAML file. We have the configuration for our certificate authority and server, client, and for the platform that we have. So in the certificate config or server config, we just dedicate the ports and the certificate path. And also for the clients, we actually we just define the configuration for the outsider networks who wants to be connected to us. So here, basically, we just register the information about the permitted blockchains. And here we have the information about our host blockchain, which is Hyperledger Fabric. And as you can see, we have different property for each host blockchain. Here you can see the properties for Hyperledger Fabric. Okay, so for visiting an actual demo of this interoperability solution, you can reach to the YouTube of Hyperledger Foundation, and you can just search automated gateways through smart contracts. Also, we have some future plans. We are trying to develop it and add some more host blockchains. I mean, we are developing the Ethereum right now, and we hopefully we can connect other blockchains as well. We also are gonna try to create some codes like bank simulations or data sharing simulations based on this library. And here is my paying respect to LFX mentorship or Linux Foundation mentorship, and you can check the mentorship on their website as well. So thank you. If you have any question, I'm all here.
Great, thanks so much. Everyone knows the drill about questions. I'll just ask you one while we wait. So the mediator, do you envision like, is that like a shared mediator or shared between like everyone that wants to go from Hyperledger to Ethereum? Or is it like everybody sort of rolls their own mediator because you have to trust it, essentially?
Okay, so let me go to my slide about the architecture. So yes, right here. So basically, the mediator is part of a relay, and relay is actually a library. So it's all developed. You just need to add relay to your code. And in the mediator, mediator actually gives you some APIs. So you have a library which has some APIs, and based on those APIs, you can manage contract call interoperability between your blockchain and other blockchains which are using this solution. So mediator is basically is just a connector between your code and the host blockchain. The only part that is different for each host blockchain is the chain connector part, or which is here the network specific part. Right now, we have support for Hyperledger Fabric, and as I said, we are developing this network specific part for the supporting the Ethereum. I hope I explained that.
Yeah. I misunderstood something, but yeah, that's great. Thanks. Okay, other questions? Yeah, Chen.
Yeah, thanks. Yeah, so thanks for your presentation. I just have a related question. What is the trust assumption behind the relays here?
Okay, so there are some points about trust. First of all, this solution is for it's not for the public blockchains, it's for the private blockchains.
Yeah.
So basically, when you, as I said, you need to have some sort of authentication, and the authentication is based on certification. So let's say I have a blockchain in a private environment, and the other company comes to me for they want to just have access to some of my services. So basically, I gonna issue them some certificates.
I see.
I'm the one who
that's the
issue the
assumption.
certificates. Yeah.
Got it. Thank you. Yeah, there might be another question on the chat.
Okay, what type of translation did you implement? Okay. In the network specific part, if I'm getting the question correctly, for the translation between the I guess I don't quite get your meaning of the translation. Do you mean the data transfer between the different relays or method invocations? If you can just elaborate that. So basically, the network specific part is just the part that we invoke different methods. So it's not really aware of the semantics. So basically, as I said, we have different smart contracts which can handle our policies. And our network specific part is actually our bridge between the relay and the smart contracts. So the mediator and actually the user who is using this library is in charge of handling the steps and the semantics that they are trying to implement. So the network specific part is basically just a mean for calling different methods on these smart contracts in order to manage the accessibility. Also, this smart contract has some information about the host blockchain, and it gets the information from the configuration part. So it knows that which smart contracts are available. It knows that which methods are available based on the information that we have here. And based on the, for example, in Hyperledger Fabric, based on the SDK of Hyperledger Fabric, it can invoke the different methods based on the scenarios and the management of the user. So here, the user, the final user, and by final user, I mean the admin of the host blockchain, is the one who decides about the communication between the network specific part and smart contracts. I hope that I answered the question and hope I got it right.
Okay, great. So thanks, Kusha. And we'll move on to the last speaker, Amir Reza Sokankash, who's also at University of Manitoba. I can see your lips moving, but you're muted.
Really?
Now you
Hello
sound.
now.
Yeah, perfect.
Okay, just let me oh, yeah, I'm trying to share my screen.
Okay, I'll let you know when we can see it.
Okay. Okay. Yeah, sorry.
No worries. You don't think it's going to work, or it's working?
No. I will present it right now. I think I fixed it.
Okay. Are you a Linux user?
No, I'm a Mac user.
Usually when people have trouble.
Yeah. Okay. So I think I have to leave the call and come back. Sorry.
Okay, yeah. No worries.
Yeah.
Okay, we'll just wait here a second. So I'll make you co-host,
Yeah.
or you can I think you might be able to share anyways. But...
Yeah. Let's see. Here. Oh yeah. Yep, fixed it.
Okay, good.
Yeah. Not co-op, sorry.
Yeah. Okay. All right. There
Right.
you go.
Yep, amazing. All right, I think you have it right now.
Yeah, looks great. That's good.
Yeah. All right, so hello everyone. Today I'm going to talk about our recent research paper, Proof of Collaborative Learning, a multi-linear federated learning consensus mechanism. So yeah, so let's dive in. Bitcoin, I'm sure as you all know, is the world's first cryptocurrency that lets people send money directly to each other without the supervision of a trusted third party, like the Central Bank of Canada. And Bitcoin is really the first technology to introduce blockchain. So a major downside of Bitcoin is that it uses so much energy to maintain the transactions. So basically, right now, the electrical energy consumption of Bitcoin is comparable to the whole country of Poland, which is scary. So the main reason behind this massive energy consumption is the consensus mechanism of Bitcoin, proof of work. In proof of work, miners try to solve a complex and yet ineffective, impractical, let's say, puzzle to add new transactions to the blockchain. So the process is necessary because it will ensure that all the transactions added to the blockchain are verified and they prevent fraud, such as double spending. So miners find this solution, the solution to this complex problem, by employing trial and error. So basically, they will try as many solutions as they can, and they will loop through the solutions. So to do this, they require a massive computation power and energy to mine the transactions. So a popular way to resolve this issue is to reuse the computation power for a meaningful task. As I told you, the task of trial and error to find the hash value, the answer to the puzzle, is not something fruitful, it's not something meaningful. Maybe a more meaningful task would be to ask the miners and use their computation power to maybe compute a matrix multiplication. Maybe we could require them to compute a matrix multiplication for us instead of finding the nonce value. And actually, that is a very popular study in this area. So let's just dive in and talk about federated learning for a second. Federated learning is a method for training AI models across multiple devices. So in traditional machine learning and deep learning algorithms, you sort of gather all the data you can, and then you pre-process the data and you train a deep learning model on it. The problem with this is that you have to gather the data in the first place, and you have to find a way for the data holders to trust their data with you. And that is problematic. It will bring about privacy issues. And for that reason, federated learning was proposed. Federated learning allows us to have multiple devices, and on each device, we can train a global model locally with the local data set that they have. So nobody shares their data. Instead, on each client, the client will train the model. And at some point, after so many rounds of epochs, they will share the trained local models so that the server can compute and go through an aggregation algorithm like federated averaging. And I think it's the most popular right now. Proof of federated learning. So as I told you, some consensus mechanisms have been proposed to replace proof of work with a more meaningful task. And among them, proof of federated learning is the one who proposes using federated learning instead of finding the ninth value using trial and error. So in proof of federated learning, the computation power of miners is dedicated to training a machine learning model in a federated learning model. So basically, in this network, we have entities such as requesters. Requesters, they will ask for a machine learning task, such as face recognition. They will come to the network and say, I want a model that can recognize faces. And here's X amount of money, and I will reward this to the miners who can help me build this. Then miners in the network will perform federated learning by first creating mining pools. So in each mining pool, someone will be selected as the leader and the other as the client, and they will perform a federated learning network. They will actually create a federated learning network and they will perform the training. After so many amounts of time or epochs, whatever that may be, that's, I think, custom, they will share the weights and the different mining groups will be competing for the reward. And one of them will win. If there is a second round, nobody shares their weights. So they will keep their architecture, they will keep their weights, and they will continue training. So there are some downsides to this approach. The first is that federated learning is only achieved within the mining pools. And that is problematic because federated learning was, I think, proposed for not a limited number of miners. And because of that, this system undermines the efficiency of federated learning. The second is that the requester, the one who requests mining and actually machine learning tasks, they have no control over the architecture of the model. So because mining pools decide what they want to train. And this might not be a good approach because usually people who ask for a model to be trained, they may be startups, they may be researchers, so they have something specific in mind. They don't just want something trained. And the third problem, and I think the biggest problem, is that the system isn't fair at all, because the winning global model is not shared with other groups. And whoever wins the first round has an insane amount of advantage, because if I win the first round and I don't share the weights, in the second round, I build on what I already had in the previous round. So I'm already better than everybody else, and I'm building on that. And it's especially problematic if I have been training this model for 100 rounds, and in the round 101, a new mining group is created. They can never compete with me because I've been training this for 100 rounds, and they can never win. So so we wanted to propose something that would solve these issues. So there are three issues. One, we want the requester to be able to basically say, we want this design. Second, we want something fair. And third, we want something more efficient. So while we keep that in mind, we have this proposal. First, this consensus mechanism can be installed, let's say, on any blockchain platform. So the reason behind the platform is not something we're interested in. If there's transactions to be mined, this will work on it. The second is that the requester that we consider comes in with the global model in mind. So they have a global model, let's say a CNN, and they want to train it. So the requester will request that, and the miners in our network, they have local data sets. So they have their own local data. And the local data they have is publicly available, because in this paper, we don't go through the privacy issues of sharing private data right now. So a requester comes in with a model in mind. Miners have the data set, they start training. First, they will gather some transactions to mine, each miner. Let's say miner 1, miner 2, miner 3. After that, they train. They train for a specific amount of time we call the model proposed deadline. That is custom. We define it, or anybody who is in the network or who governs in the network. So after a specific amount of time, the miners will send the hash of the trained model to the blockchain. Along with the hash of the model, they will send some test records of their own data sets. However, the test records are unlabeled. I will explain why these test records exist, but right now, let's just accept that. After that, the smart contracts, after the model proposed deadline, the smart contract will gather all the test records that it got from the miners, and it will send it to the miners again. So basically, I am miner 1, I sent some test records, miner 2 sent some test records, miner 3 did the same. As miner 1, I will get the unlabeled test records, the inputs of miner 2 and 3, not myself. And this will happen for miner 2 and 3 again. Then, as a miner who trained, I will feed the test records of other miners to my model. So I will basically get the prediction of their test records. And I will send that prediction to the smart contract as fast as possible. There's a deadline for this as well. We call this prediction proposed deadline. And that exists because we don't want the miners to be able to perform some unsupervised learning tasks, actually algorithms, on the test records they get from the miners, from other miners. So they send the predictions. After that deadline, the predictions are gathered again, and it will be sent to the responsible miner. So as miner 1, I sent my test record to miner 2 and 3 through the smart contracts. And then after the prediction proposed deadline, I will get the predictions they made. So I will get the predictions of miner 2 and miner 3. Because I have the labels of the test records I sent, I can say whether miner 2's model is better than miner 3 or the reverse. So I can rank the miners, the other miners. So each miner will rank the other miners. This is what we call vote proposal. They will vote, let's say, based on 2 things. First, accuracy or loss. Second, the time of the made prediction. After that, they will vote. So let's say that miner 2 had lower loss than the miner 3. So in my ranking, miner 2 is better than miner 3. The votes will be sent to the smart contracts, and they will be combined. So using that, we can select the winners. So whoever has the most number of votes, they will be the winners. But we don't have one winner in the system. We have K number of winners. And we have that because of a reason, because federated learning happens between multiple devices. So we have to have multiple winners because we want to provide the aggregation as the global model. So we select the K number of the K best winner, the K best miners as winners. Then we will create the block. The block contains the transactions of all winning miners. So miner 1 has 2 transactions, miner 2 has 3 transactions, miner 3 the same. So we will aggregate all those, combine those into one block, and we will add that block to the blockchain. At last, we will reward the miners. A specific contribution of this paper is the rewarding mechanism. we reward the miners based on the significance of the contribution they made to the global model. So basically, if we have a deep neural network with 10 million parameters, okay, if a winner miner made 1% difference to one parameter out of all 10 million, it will be rewarded accordingly. Because it will not be fair to reward this miner the same as a miner who won in the initial round and made so significant difference to the global model. And that is our reward mechanism. Attacks and security. So a possible attack on our system would be for the miners to don't train at all and just make predictions based on some unsupervised or even supervised learning tasks other than the deep learning training that we define. And in our paper, we fully proved that this will not be the case. And even if this happens, they will not win the round. And because of that, the security of our system remains unbreached. Results. So we experimented with our system. First, we distributed the dataset of CIFAR10 between 10 miners equally, and then trained the whole thing. So as you can see, this is the validation loss, and all miners are converging. And as for the other results, so if you remember, we wanted to create a system that is both fair and secure. So in the plot on the right, we can see that we first distributed the data a little bit different. So miners 6 to 10 had 4 times the amount of data set than miners 1 to 5. Then we started the network, we let them train and mine. So after 20 rounds, we stopped the network, and we can see that miners 6 to 10 won less rounds than miner 1 to 5, even though they had more data sets. They had more data records, sorry. So, and this is really surprising, but it makes sense. These miners had more data set, and in the initial training rounds, they made so much contribution to the data that after, let's say, 7 rounds, the global model was more interested in the data records of other miners, even if it is super small, than the data set of these miners. So they stopped winning, but the contribution they made to the global model was so significant that using our reward mechanism, we can see in the last plot here that they were more rewarded in the whole system at the end, even when they won sometimes twice as each other, they were more rewarded. As for the security, we performed some security attacks using the KNN algorithm. We also use the adversaries, which are miner 1 and 6, where one of them has 4 times more data records than the other. We also used 2 other attacks. So basically, if these adversaries won the round, they would ruin the performance of the model because they would send weights that are equal to 0 to the global model. If we did that and it was combined in the whole global model, it would have ruined the performance. Second, they used KNNs and they didn't predict. And third, they voted backwards. So if, let's say, miner 7 had the best predictions, they would have made the worst vote for miner 7 to undermine the performance of the model. And as you can see here, none of them won any round. So that's pretty good for us. And these are the small references for this paper because we mainly introduced our own concepts. And thank you so much for listening. If you have any questions, I would be happy to answer to. This work is the result of our work in the TCDT lab at the University of Manitoba. Thank you so much.
Great, thanks. Any questions for Amir Reza? I'll ask one. Would it make sense to decouple the block creation from the reward mechanism? So you could imagine, for example, you solve, like you do your whatever federated learning task and you just get tokens, but then you have a separate consensus mechanism, which is just a proof of stake. So you can stake those tokens and then participate in consensus if you want. And so the miners could be a distinct entity from the people that are doing the work.
Miners could be distinct from people who are training. Is that what
Exactly?
will
Yeah.
be?
Yeah. So you train
Yeah.
to earn tokens, and then block creation is done by people who stake tokens.
Oh yeah,
So
we
you could
can
do
do
one
that.
without the other. You wouldn't have to do both.
Yes, we can do that. I think we can do that.
It might, yeah, it might make sense to explore. But anyways, there's a question in the chat as well.
So how do you elevate the non-determinism of training and prediction among different miners? What are the assumptions? Non-determinism of training. Could you please explain a little more? If we're referring to the fact that I think deep learning models. Oh, so basically we are rewarding the best of the best. So who wins is not our problem. Who wins is basically because if we have the same weights, the output of the model is the same, so it's deterministic. But what local model is trained in each miner is not something we're concerned about, because even if the performance of all miners is not as good as what we want, this is what we have right now. There's a problem with the data, or there's a problem with the global model. This is if the hardware is different, the prediction is different. No, actually. So basically, the weights, if the weights are the same, the weights are what determines the weights of the deep learning model are what determines the outputs, not the. So you can have you can compute the output of a test record using whatever hardware you have, because it's basically a matrix multiplication. So the answer is always the same. The training it might not be, but the prediction, yes. Oh, there's a time difference. Oh, I think I understand your question right now. So the prediction proposal time, if you're referring to that, the prediction proposal deadline is a custom number, and we have an admin in the system, but the responsibilities of the admin can be distributed. However, the admin will sort of define this prediction proposal deadline according to the capabilities of the miners, being hardware. Yeah, thank you so much.
Okay, and thank you as well for presenting.
Yeah, thank you.
All right, so then that brings us to the conclusion of BTS 2024. So thank you to everyone who participated, spoke, asked questions, just listened, and it was great having you all. I'll leave you with Chen, and he's going to say a few words about BTS next year.
Yeah, thanks a lot, Jeremy. So first of all, thank you for all your effort in this event, and we made it. Nice. Yeah, we have wonderful speakers, scholars, and students. At least I'm so happy about today's event. Now let's look forward. will happen next year. We have some decisions. So maybe I can share some link and quick notes. So decision number one is that we want to have our in-person BTS next year, right before something called Summer Institute. Right, for those who don't know Summer Institute, it's an event, it's a 2-week event organized by Blockchain at UBC. Right, this year it will be in Switzerland very soon, maybe early next month. Right, next year it will back to Vancouver campus, and it's an interesting oh.
Sorry, I was just going to say you sent the link just to me because we were DMing.
Oh, sorry. Yeah,
Zoom's
thank
a
you.
bad
Thank you.
internet.
Yeah, Jeremy. Yeah, I thought, I didn't notice, only sent it to you. Thanks. So yeah, so this is a link to the Summer Institute, right? And next year it will be at Vancouver campus, right? Maybe in June or July, and we will see. We haven't decided, right? Once we have decided the Summer Institute, and it will be right before our Summer Institute. So please stay tuned. Now I want to present. So this is the reason number one, right? Why and we choose the particular location and the particular time. So 2.5 reasons. Reason number one, right? Reason number two. Previously, I was thinking to have our BTS in Kelowna, and then I think maybe it's not ready. Maybe we'd better wait for a few years. Why? Because starting from last year, the wildfire is a bigger problem, right? Often in June, July. So last year, I still remember that, and even in the in the midnight, I had to take my students to run away from Kelowna. So hopefully, right after a few years, the wildfire issues will be solved, and then summertime, Kelowna will be, I would call it a beautiful place. Right, we have wineries, we have these beautiful lakes, right, and we have many interesting activities there. Maybe kind of after several years, right? And we will have in-person BTS in Kelowna. And finally, half reason, we just had a workshop at Vancouver campus. I believe I attended that, right? I was part of the organizing team. I think most attendees were very happy about the workshop. So we have a good example. Okay, to sum up, please stay tuned, right? After we finalize the dates, and we will send everyone, right, our update, through, right? And Jeremy, I believe, right, you have a mailing list or something like this. Yeah, and it will be interesting, and hopefully, right, and maybe we will have some student oriented, some fun activities, right? Because it has been a while for us to have an in-person BTS. And I will try my best to make it fun and interesting, especially for our scholars and our students. Yeah, that's all from UBC side. Very look forward to seeing you next year. Yeah, thanks, Jeremy. That's all.
Awesome. Okay, yeah, we're all looking forward to it as well. Okay, well, that's it. So thanks everyone again, and we'll hope to see you next year.